Welcome aboard, Sleepy Voyager. Where in the world are you watching from tonight? Berlin, Bogota, Brisbane? Drop your location in the comments so our little starship feels a bit closer. In this episode, we'll explore how something unusual just happened to interstellar visitor 3I Atlas, while the sky seemed to erupt. Two sudden novae, powerful solar storms, and a week that felt stranger than chance. I'll guide you through what's confirmed, what's likely, and what's still a mystery. Soft, steady, and sleep-friendly. Begin by picturing a simple clock sweeping through 3 rotations, 72 hours, while the world goes about its ordinary business. A kettle boils, a bus sighs at a stop. Somewhere far south, an observer steps into cool pre-dawn air and lets their pupils open to the dark. In that span, 4 threads begin to braid themselves together. Starlight brightening from eruptions long ago, the ground trembling along a complicated seam, the sun exhaling great billows of plasma, and a visitor from another star system gliding through our neighbourhood as if it had always known the way. The first thread starts with a pinprick that wasn't there the night before, or if it was too faint for human eyes to notice. On September the 23rd, in the southern sky, a star labelled V1935 Centauri swells in brightness until it reaches the edge of naked eye visibility for people with dark horizons. It isn't a new star at all, but a quiet system jolting to life, photons walking to us across thousands of years to arrive just now, in this exact week, touching the backs of our eyes with the news of a thermonuclear flare that happened long before any of us learned our own names. Around the same time, instruments in orbit respond the way tuning forks answer a clear tone. Space telescopes pivot. They collect high-energy signals. They mark the eruption's signature in the ledger of the sky. As this brightening settles into our awareness, a second spark lifts itself from the background. V7994 Sagittarii, another nova, in a neighbouring swath of the southern constellations, steps up out of the haze of faint stars and announces itself. Not dazzling, not theatrical, but undeniable. A soft new point that wasn't there for the casual eye and now is. 2 separate systems, 2 separate distances, 2 packets of ancient light that happen to crescendo within days of each other, like distant bells that, through some patient alignment, ring close enough together that we notice the harmony. Then, while most of the world eats dinner or checks the lock on the door, a different clock ticks. On September the 24th at 22:21 UTC, the crust beneath northwestern Venezuela slips. The motion is quick, always quicker than it feels, a matter of seconds for the fault to break and the elastic energy to go rushing outward as waves. At a depth of just a few kilometres, the force couples efficiently into the surface where people live, turning bedrock into a messenger. Buildings sway, glass hums softly in frames. The human nervous system, sensitive to unexpected motion, writes the memory with a bright pen. Emergency teams look at their watches. Sensors forward their numbers. Maps blossom with concentric lines that mean this is where it felt strong, and this is where it faded. The night does not end with calm. A few hours later, in the early UTC morning of September the 25th, a second rupture takes hold nearby. Slightly deeper, measured a touch larger. To a geophysicist, the pairing is familiar. Stress redistributed by the first event nudges a neighbour across its own threshold. The Earth does what it has always done, converting slow accumulation into sudden correction. To everyone else, it is simply unnerving to feel the same story retold before sleep has had time to smooth out the first. Above this, strand 3 unfolds in a medium far thinner than air. The sun is at an excitable phase of its cycle. More freckles on its face, more twisted loops of magnetism, more sudden releases where fields snap and reconfigure. Coronal mass ejections, great buoyant clouds of charged particles, are launched into the inner heliosphere like weather fronts in a windless ocean. Models, built from decades of watching and testing, carry these clouds forward on a grid and estimate where and when they will drift past planets and spacecraft. Their paths look soft on the screen, like breath on glass, but the physics is crisp: speed, density, orientation of the embedded magnetic field, and how each of those might change as they intersect the invisible domains around worlds and instruments. Moving through all of this is the fourth thread, the one that gives the week its uncanny focal point. 3i Atlas, an object not born here, on a hyperbolic path that will carry it past us and back into the dark between stars. It doesn't hurry. It follows its own geometry, steeply retrograde, skimming the same ecliptic plane where planets do their laps, presenting for once an interstellar traveller in a place our tools can reach. No close calls, no danger, just proximity of the scientific kind. A few tenths of an astronomical unit from Mars in early October. A comfortable, study-friendly distance from Earth later in the year. This timing matters because it means when the sun exhales, there is something unusually interesting in the path of the breath. Think of this 72-hour span not as a crisis, but as a layered score, each line advancing at its own tempo. The nova light arrives after millennia, and yet to us it looks immediate. The earthquakes release decades of stored strain in a minute, and yet their aftershocks will outline the faults like slow lightning for weeks. The solar eruptions blossom over hours, traverse planetary distances in days, and then play out in auroras and radio hiss and little nudges on spacecraft orbits. The interstellar visitor takes months to cross the region we can easily watch, and in that passage we get to test our expectations against something that did not form under our sun's rules. It helps to place moments on a simple tape. First, a quiet watcher in Australia, Chile, South Africa, or on a ship at sea could, under darkness, raise their eyes and notice that Centauri was carrying a bright mote not visible a week ago. Next, an alert arrives from a seismic agency. The numbers are steady, and they mean motion in Zulia. The headlines will simplify, but the details are there for anyone who wants to see how depth modifies shaking, and how magnitude is not the whole story. Overlapping this, a set of solar images that look like flames filmed in extreme ultraviolet, where loops bloom and relax. A forecast panel that says a disturbance will reach a certain radial distance on a certain date with a margin for error that we mark honestly. Threaded through, observatories, both professional and amateur, turning to a faint fuzzy point that is not a star and not ours, cataloguing its brightness, colour and tail. What makes the cluster feel unusual is not that any single piece is unheard of. Novae occur every year. Mid-6 earthquakes happen, sometimes in pairs. The sun breathes like this around its maximum, and models keep pace with the rhythms. A cometary interloper, while rare, has visited before. It's the way the rhythms overlap, the coincident crescendos. Our minds notice the way you notice when two distant trains sound their horns within the same half minute, and the intervals happen to match. We are built to track that kind of alignment. We are comforted when it means something. We are unsettled when we cannot tell if it does. So we move gently and we sort. We lay down markers, September the 23rd for the first nova's rise to the edge of naked eye visibility, September 24th at 22:21 UTC for the first Venezuelan rupture, September 25th at 3:51 UTC for the second, the same window for active coronal mass ejections leaving the sun with the deliberate speed of a slow storm that is still unimaginably fast compared to anything we build. We place 3i Atlas on its lane, inbound toward an October 3rd encounter geometry with Mars orbiters that might give us spectra and light curves worth saving and comparing for years. Between those markers, we add texture. We imagine a backyard telescope and a small one, nothing fancy, pulling a haze out of the background where the interstellar object moves a fraction of a degree from night to night. We imagine a living room where a light fixture ticks against its mount, just enough to be noticed by someone who has never felt it move before. We imagine a control room where a radio spectrogram shows the ionosphere changing character as the sun's output folds into the Earth's magnetic field in just the right orientation to crack open a little extra connection. We imagine a researcher somewhere with a mug of tea overlaying the graphs. Brightness versus time for two novae, seismic energy release versus hours, solar wind speed versus radial distance, comet magnitude versus heliocentric distance, with a pencil note about phase angle and dust production. None of this demands a grand conclusion. It asks only to be mapped carefully. To say, here is the order in which the lights came on, here is when and where the ground shook, here is how the solar wind thickened and thinned, here is the path of the visitor. It invites the kind of attention that slows the pulse rather than quickens it, because attention is how we keep wonder from becoming worry. If we can place each event on the same quiet canvas, we can notice what is remarkable without insisting it be miraculous, and we can let the next days bring whatever detail they will, while we continue to watch, measure, and breathe. Before dawn, the air is still and salt-sweet along a low river in New South Wales. A small roll-off shed opens. A red headlamp moves like a patient firefly. The observer has done this 1,000 times. Level the mount, breathe, let the sky settle into focus. Centaurus rides low, its brighter stars stepping up from the horizon like the edges of a sleeping continent. Between charted points, so familiar the hands can sketch them from memory, there is a prickle, a grain of light where last week there was nothing to linger on. The habit, drilled by countless quiet mornings, is not to rush. Centre the field, blink the view against a printed atlas and a digital chart. Compare brightness to a nearby star of known magnitude. Let the eyes rest, then check again. The number that forms is not spectacular, around magnitude 5.8, but it means a threshold has been crossed. Under truly dark skies, a careful, dark-adapted eye could catch this without binoculars. That alone is enough to quicken the breath, not with alarm, but with the soft energy of a discovery that knows exactly how loud to be. A message goes out, crisp and spare, the way such things are. Coordinates, time, filter, estimated magnitude, equipment used. It joins other messages moving at light speed through fibre and air toward the places where transient events are triaged. The same starfield is examined on other continents a few hours later, then again and again as night slides west around the world. Confirmation is not dramatic, it is built on agreement. A brightness estimate within 1/10 of a magnitude here, a spectrum there, the faint scaffolding of hydrogen emission lines saying yes, this is a nova, and no, it is not a minor software phantom or a flare star caught mid-blink. The Central Bureau posts a notice. Observers fold it into their lists. A handful of space-based telescopes mark their schedules with a quiet reorientation. From orbit, the signals are less romantic but more revealing. A gamma-ray instrument that watches the whole sky registers an uptick from the nova's direction. High-energy photons riding in from the same patch of Centaurus, whether the ground observers have been measuring a steady green-white point. An X-ray telescope built to swing at short notice slews and begins to count hard X-rays, evidence that the newborn shock is accelerating particles and heating plasma to millions of degrees. This is one of the surprises of the past decade of nova science. These eruptions are not only pretty optical events, but capable of launching charged particles to near-light speeds and lighting the high-energy sky for days. On the ground, the simplest idea is often the best place to rest for a moment. A nova is not a star tearing itself apart to die. It's a star's dense remnant, a white dwarf, Earth-size but sun-massive, collecting a thin blanket of hydrogen siphoned from a nearby companion. In that blanket, gravity compresses and heats the gas so relentlessly that a tipping point is reached. Fusion begins not as a gentle core burn, but as a runaway at the surface, and the thin shell detonates. In seconds to minutes, the system brightens by thousands to tens of thousands of times. The white dwarf survives. The companion survives. The accumulated skin is hurled into space at thousands of kilometers per second, and for a while the binary becomes one of the most interesting objects in its neighbourhood. Measured through a small telescope, this physics plays out as a light curve you can draw with a pencil. First, a quick rise toward a maximum, then the decline, sometimes steep, sometimes a lingering slope, sometimes broken by plateaus or small rebrightenings, as different layers and processes contribute. Observers like to time how long it takes to fade by 2 magnitudes, then by 3. Those T2 and T3 times classify the nova as fast or slow, hints about the white dwarf's mass and the envelope's opacity. Beneath the brightness, the spectrum evolves too. Early on, with the ejected shell still thick and expanding, broad hydrogen Balmer lines are smeared by that speed, like words stretched on a rubber band. As the gas thins and cools, helium and nitrogen features flower, forbidden lines bloom in the low-density conditions, and the whole profile narrows and shifts with the shell's changing pace. For the calm backyard astronomer, there is practical craft in all of this. If the sky is dark enough, this nova can be estimated visually, no camera, no filter, using comparison stars from a charted sequence. A notebook gets a date, a time, UTC keeps everyone in the same conversation, a magnitude estimate, and a brief note on conditions. Good seeing, thin cirrus low S, strong dew by 0-300. If there's a camera, a V-band filter makes the measurements more comparable with other observers. The routine becomes its own kind of meditation: center, focus, expose, plate solve, measure, report. Hundreds of such points scattered from living rooms and fields and patios cohere into a curve that large telescopes alone could never draw. Big instruments have many demands, but committed amateurs can give a nova their whole night, then their next night, and the one after. In professional spectra, the line widths tell a story of speed. 5,000 km per second reads as a hydrogen emission profile broadens so much that its edges feel less like a line and more like a low hill. Substructure, the slight shoulders and kinks in those lines, betrays clumps in the flow, places where faster material runs into slower material and a shock forms within the ejector. Those internal collisions are one way to feed the observed gamma rays. The shock accelerates particles, and those particles radiate as they spiral in magnetic fields or collide with other particles. Whether the emission is dominated by electrons, leptonic processes, or protons and heavier ions, hadronic processes, is not a question that puts anyone to sleep easily. It's the kind of puzzle astronomers like to carry around for a few days while new data accumulates. Behind the immediate observations lies a longer geometry. The nova's light began its journey thousands of years ago. The photons that strike a camera sensor tonight left when human beings were carving the first long stories into memory and stone. That light travelled through dust that reddened it a little, through swaths of interstellar medium that left faint absorption fingerprints across the spectrum. Distance estimates are always a little slippery at first, tugged this way and that by assumptions about how bright the nova should be at peak and how much foreground dust dims it. Parallax from early survey missions helps if there's a reliable measurement of the quiescent system. Otherwise, astronomers turn to the ensemble of similar novae, building a gentle argument out of many imperfect clues. Down near the horizon where Centaurus climbs, the practicalities matter. Extinction through all that air steals brightness to ness and contrast. Heat from a nearby roof wobbles the star's image. On some nights, a low bank of cloud rules out everything except the basic act of stepping outside and checking. On others, the air is steady, and the nova can be held like a bead between two comparison stars while the mind counts and compares. Fainter than this, brighter than that. Those small human acts, multiplied across longitudes, make it possible to catch subtle changes. A dip that hints at early dust formation as carbon condenses in the cooling flow. Or a flicker, a few tenths of a magnitude over hours, that might mean the shock has re-energized the shell. As the hours accumulate into days, the nova's persona changes. Radio arrays point and begin to hear free emission from the warm ionized gas. Later, sometimes synchrotron emission whispers of electrons that have truly been launched to high energies. Infrared instruments look for the warm glow of new dust if it forms. Ultraviolet spectrographs trace the ionization state as the central source hardens and then softens. Each band of the spectrum, like a different section of an orchestra, comes in on cue, holds a passage, then yields the theme to another. There is music too, in the cadence of the human network that watches, an alert on a phone at breakfast. New spectrum uploaded, strong EI, N2, emerging. A late-night post from someone under Chilean desert skies with a perfectly flat field and a curve you could hang a lesson on. A note from an observer in South Africa that dew heaters failed, and a second set of frames came out soft, accompanied by a promise to try again tomorrow. The modest heroism of it, the repeatability, the humility of small measurements, builds a collective instrument that can play along with the largest mirrors and the most precise satellites. For those wanting to see it with their own eyes, the sky offers a simple teaching about magnitude and darkness. Magnitude 5.8 rides the edge of naked eye visibility, only in rural darkness where the Milky Way looks like milk and the horizon's a clean line. In suburban light, binoculars turn the trick instead, gathering a little more light and pulling the nova out of the background. A small telescope at low power is kinder than a large one at high power. Novae are most themselves when seen in context, set in their star fields like a single bell in a tower rather than under a microscope. The reward of that context is scale. To see the newcomer against a grid of old stars and feel the mixture of new and ancient in the same view. While the object is bright, spectroscopy accessible to amateurs becomes possible. A simple transmission grating in front of a camera will smear the nova's light into its spectrum. Even if the lines are not crisply separated, the broad bright hump where hydrogen sits will be visible, and a novice can learn the taste of it. The way an emission line object makes a spectrum look like a series of lanterns instead of a continuous rainbow. Over a week, that spectrum changes. A person who takes the same kind of data from the same place at the same hour, night after night, will be able to build a little flipbook of physics, and the flipbook will be worth more than the sum of its frames. Far away from backyards, numbers run. Hydrodynamic models take a white dwarf mass, a composition and accretion rate, and they calculate an envelope that heats and runs away. Radiative transfer codes take an expanding shell and ask how light makes its way out. Shock models layer a faster wind over earlier, slower ejector, and ask how much gamma ray and X-ray power the collision can extract. None of these codes are bedtime reading, but they're outputs, curves and synthetic spectra that can be laid on top of the real ones, allow quiet conversation between theory and sky. Adjust a parameter by a small amount and watch how the peak shifts, how a line brightens, how a decline steepens. Bring it closer to the measured curves, then stop adjusting and wait for the next night's data to confirm or contradict. The nova's position in Centaurus is a gift to southern observers and a challenge to northern ones. In Europe, the view is low and easily lost in haze. In Chile and Australia, the object rises to a respectable height, where the air is thinner and the seeing gentler. This geographical asymmetry is useful. It means the object can be followed for longer arcs each night from the south, and when the north loses it to weather, someone below the equator can pick up the thread. The planet's rotation stitches these arcs into continuity. If the nova is truly energetic, there is a chance, just a chance, for dust to form in the ejector. When it does, a well-behaved decline can pause and even dip, as if someone has drawn a translucent curtain across the lantern. In infrared, that curtain glows. In optical, the nova dims. Weeks later, as radiation and shocks erode or disperse the grains, the curtain lifts. Catching that behavior requires patience and luck. Missing it is no failure, only a reminder that these events remain, in important ways, individuals. In the catalogue, V1935 Centauri will one day be no more than a line, a date, a few numbers and references. In memory it will sit where it first announced itself, a barely there brightening at the edge of what the eye can hold, made real by the act of writing it down and by the chorus of people who looked up on the same night from far-flung dark places and agreed, yes, there is a new light here, and yes, we will keep watch while it changes. A few nights after Centaurus surprised careful eyes, the archer lifted his bow above the horizon, and something faint but insistent glowed where there had been only background before. Sagittarius is a busy place, dense star fields, dark lanes of dust, the Milky Way running like a river through it, and that crowdedness makes new lights harder to spot. Yet there it was, a point that refused to stay anonymous, rising to around magnitude 6.2 and asking to be measured rather than admired. The method is the same as always: center the field, compare with nearby stars of known brightness, write down what you see. But the setting adds difficulty. In Sagittarius, the sky is rich enough that a small mistake in identification can propagate, so observers slow down, replate solve their frames, and verify the same coordinates with two charts before sending a single number. The sensation with a second brightening so soon after the first is not shock so much as alertness sharpening another click. 2 novae within days isn't unprecedented, but it is uncommon to have both flirting with naked eye territory. In a dark sight, a patient dark-adapted eye might lift V7994 Sagittarii out of the grain of the Milky Way without optical help. In suburban glow, binoculars or a small telescope make it plain. Observers in the southern hemisphere are favoured again. The object climbs higher, the air column is thinner, and extinction steals less light. From mid-northern latitudes, the object lives low, where haze, heat ripples from rooftops, and horizon glow all conspire to sand-down contrast. There, photographs and careful calibration do the heavy lifting that the eye cannot. As measurements accumulate, the light curve begins to sketch itself. Perhaps the rise is a touch slower than the Centaurus nova, perhaps the decline starts steeper. Each nova declares its personality in the first several nights. Those T2 and T3 times, the days to fade by 2 and 3 magnitudes, go into a small table that lives in many notebooks, rough guides to the white dwarf's mass and the opacity of the ejected envelope. A faster decline often hints at a more massive white dwarf and higher ejection velocities. A slower, more languid fade can mean a thicker, more opaque shell. The numbers are gentle suggestions, not verdicts, and they invite more data rather than closing the case. Spectroscopy gives the second nova its voice. Early spectra in many novae are dominated by broad hydrogen Balmer emission with P Cygni profiles, an emission peak with a blue shifted absorption notch, signposts of an expanding outflowing shell. In some, iron lines, the Phi2 class, fill the spectrum with a forest of features. In others, helium and nitrogen, He/N, step forward strongly, often associated with higher velocities and more energetic outflows. Which path V7994 Sagittarius takes will show itself over days. Phi2 novae tend to evolve more slowly and can build dust later. He/N novae often change quickly and can be stronger emitters at higher energies. The class matters because it guides expectations for radio and gamma ray behaviour, but it is also simply satisfying to watch the lines brighten, narrow, and change shape as the shell thins. That shell is not a smooth balloon. Velocities of a few thousand kilometers per second spread the lines into wide hills, and subtle kinks in those hills betray structure. Faster material overtaking slower material, creating internal shocks. Those shocks are efficient at accelerating particles, and in recent years several novae have revealed themselves in gamma rays as those particles radiate. No one needs to assume anything exotic to account for it. The mechanism is the familiar one from other astrophysical shocks, scaled to a nearby short-lived laboratory. Hard X-rays can follow for a while, produced by the same shocks heating plasma to tens of millions of degrees before the system softens and the emission slides to lower energies. Observationally, Sagittarius complicates and clarifies at the same time. The line of sight dust in this direction can be significant, reddening the nova's light and dimming it by an amount that varies across the field. Photometry teams account for this with colour terms and by choosing comparison stars with well-known colours. Spectroscopists can estimate the extinction from line ratios and continuum shape, then de-redden the spectrum to peer closer to the nova's intrinsic output. That de-reddening also helps with distance estimates, though help is a modest word here, and these distances for novae are famously slippery without good parallax of the progenitor system. The old practice of tying peak brightness to decline rate has been questioned in detail for years. More often now, teams assemble a distance estimate from several threads, parallax if available, extinction maps, expansion parallax of the ejector in resolved images, and comparisons to well-studied analogues. On small mounts and big ones, the same rhythm takes hold: point, focus, expose, reduce, submit. A single observer can contribute meaningfully to a nova's story by keeping their setup the same night to night, so that their measurements are internally consistent. A whole network can stitch those threads across longitudes to build continuous coverage. In the first week, cadence matters because short timescale features, flickering at the level of a few tenths of a magnitude, brief plateaus or a shoulder on the decline, can hint at geometry and physics inside the outflow. A plateau might indicate a phase where the pseudo-photosphere's radius holds roughly constant while the temperature changes. A dip followed by a recovery could point toward early dust formation and then clearing. If dust does form, and Sagittarius sightlines make it likely we'd notice, optical brightness can sag while infrared rises as fresh grains absorb and re-emit the nova's light. Polarimetry, even simple low-resolution work, can catch the scattering signature of asymmetric dust and gas, telling us that the outflow is not a perfect sphere but a structure with preferred directions, equatorial enhancements, bipolar flows, clumpy knots. Later, high-resolution imaging with large telescopes might actually resolve those shapes, years down the line, but in the bright days the signatures are all spectral and photometric, etched into line shapes and light curves. Radio arrays wake up a bit later than optical telescopes. Thermal free radiation peeks through, first from the ionized gas. If non-thermal synchrotron appears, it testifies that electrons really have been pushed to relativistic energies in shocks. The timing of those radio components relative to the optical decline helps disentangle density and velocity structure in the ejector. Meanwhile, ultraviolet instruments, when they can be scheduled, give a brisk accounting of ionization states and abundances, catching lines that are either invisible or blended in the optical. Each band holds a piece of the same event, and each piece is easier to interpret when the simple nightly optical measurements give the context of what the nova is doing overall. Human context accumulates alongside the data. Someone under Namibian skies sends a plot where the nova's brightness has clearly pivoted from rise to early decline. A team in Chile posts the first decent spectrum with unmistakable P Cygni troughs, and their velocities make other observers recalibrate their expectations for how quickly features might evolve. A backyard in Queensland contributes a run of unbroken, cloudless nights that catches a mid-evening flicker no one else saw because of weather. Later, that flicker lines up with a small spike in X-rays and becomes a clue rather than a curiosity. Under the eyepiece, for those who prefer the directness of photons on the retina, the nova changes character as the moon waxes and wanes, as the Earth turns, as the air steadies or shivers. Low power, wide field views are kindest, letting the object sit in its starry neighbourhood so the mind can compare it to familiar anchor stars without fuss. A finder chart annotated with magnitudes becomes a companion. After several nights, the pattern of comparison stars feels like a small song the hands can hum while the estimate settles. The ritual, note the UT, the conditions, the magnitude, has its own comfort, a steadying shape imposed on a transient event. Behind the scenes, models whisper possibilities to observers looking for specific signatures. If the nova is Phe2- type, a later transition to nebular lines and the potential for dust would not be a surprise. If E/N, faster evolution and stronger early high-energy emission become reasonable guesses. If internal shocks are strong, then gamma rays may be more likely. If the velocity distribution is narrower, the non-thermal contribution could be muted. None of these are absolutes, all of them benefit from more data, and the happiest path through them is a light grip. Watch, measure, test, and be ready to be wrong cheerfully. Geography gives this nova the same tilt as the first, the South sees best. In Argentina, Chile, South Africa, Australia, and New Zealand, the object rides high enough for long, clean sequences. In North America and Europe, it keeps its secrets nearer the horizon, but even there, a clear morning or evening window can add valuable points to the curve. The global mesh of observers, some professional, many not, makes a strength of that unevenness. When one region clouds over, another may be clear, and the nova doesn't know to pause while weather moves across continents. If we place this second brightening into the broader week, it sits like a second bell struck, not long after the first, the two tones overlapping. Instruments already turn to the sky for V1935. Centauri can pivot a small angle to collect the newcomer. Catalogues make room for another entry. Schedulers at observatories ask whether to trade an hour from a planned program for a quick spectrum here. A few photometric points there. The justification is easy. Bright novae are rare enough that every well-sampled one teaches something new, and two within a week give an almost laboratory-like comparison under similar seasonal and space weather conditions. For those following the larger tapestry, solar storms, earthquakes, and the progress of 3i Atlas, this nova is a reminder that stellar stories have their own clocks. Its photons started toward us long before the rest of the week assembled, and their arrival now is an accident of distance and geometry rather than a signal from any terrestrial or solar system process. That recognition is not demystifying, it is steadying. It lets us give the object our full attention on its own terms. A white dwarf and its companion, a thin shell gone unstable, a shock expanding into space, and a transient light in a crowded constellation that, for a handful of nights, lets the human eye see the physics of a binary system written directly on the sky. Begin with a pair that looks ordinary from a distance, a compact, dim star that has already spent its central fuel, and a larger, softer companion still donating light to the night. The compact one is a white dwarf, roughly Earth-sized yet with a mass comparable to the Sun's, its matter packed so tightly that a teaspoon would outweigh a mountain. Its gravity is immense, the kind that raises tides on its neighbour not with the oceans, but with starlight itself. Between the two lies an invisible boundary called the Roche lobe, a teardrop-shaped zone of gravitational influence. If the companion's atmosphere swells enough to graze that inner point between them, gas can spill through like sand through an hourglass. That narrow pass, the L1 point, becomes a stream, and a stream that close to a compact object does not fall straight in. It misses, curves, and spreads into an accretion disk, a luminous whirling skirt of hydrogen and helium spiralling toward the dwarf. Sometimes the white dwarf's magnetic field is so strong that it yanks the stream out of its graceful disk and funnels it along the invisible rails straight onto magnetic poles. Those systems are called polars. Weaker fields make intermediate polars where a stubby inner disk survives. In many others, magnetism is gentle, and the disk forms cleanly, converting gravitational energy to heat and pale light as it shuffles angular momentum outward and a mass inward. Night after night, the disk lays a feather-light skin of hydrogen onto the dwarf surface. The skin is thin by stellar standards, a few meters to tens of meters thick, but under a surface gravity hundreds of thousands to 1,000,000 times stronger than Earth's, it is compressed with relentless intimacy. Here, the physics turns beautifully counterintuitive. Inside a white dwarf, matter is degenerate. Its pressure does not primarily come from temperature, the way the air in a bicycle tyre does. Instead, it comes from quantum mechanics, the refusal of electrons to all occupy the same state. This matters because when the hydrogen skin heats up, its pressure does not rise enough to allow a gentle expansion that would regulate the burn. In ordinary stars, heat makes gas expand. Expansion cools the gas, and the thermostat remains stable. On the surface of a white dwarf, heat does not unlock breathing room in the same way. Temperature climbs, but pressure barely budges, a thermostat with the dial snapped off. As the skin thickens and is squeezed, its base temperature creeps upward. Hydrogen fuses via the CNO cycle, where carbon, nitrogen, and oxygen act as catalysts to speed the fusion of protons into helium. That fusion releases energy. Energy raises temperature. Higher temperature accelerates the reactions, positive feedback. In degenerate conditions, this becomes a runaway, a thermonuclear flash. The transition from quietly storing fuel to brief stellar volcano happens quickly by astronomical standards, over seconds to minutes. A burning front races laterally through the skin and vertically outward, igniting the layer and sending a shock into space. The white dwarf is not destroyed. It is scalded, then briefly wrapped in a luminous, expanding shell. The shell's expansion produces several signatures we can feel with instruments. In the optical, the system brightens by factors of thousands to tens of thousands, climbing to naked eye thresholds if dust and distance permit. The spectrum wears broad emission lines, hydrogen's Balmer series, helium, and later nitrogen and oxygen smeared by velocities of hundreds to thousands of kilometers per second. Often those lines carry P Cygni profiles, with an emission peak at the rest wavelength and a blue-shifted bite taken from it, absorption by gas blowing toward us, silhouetted against the nova's own hot pseudo-photosphere. The profile's depth and shift sketch the outflow's speed and density, a stenographer's shorthand for a supersonic wind. The light curve, the simple graph of brightness versus time, becomes a story you can sketch by hand. A brisk rise to peak, then a decline whose speed, measured by T2 and T3, the number of days to fade by 2 or 3 magnitudes, whispers about the white dwarf's mass and the ejected layer's opacity. Fast novae, small T2, T3, tend to live on heavier dwarfs with more compact, hotter skins. Slow novae linger, their thicker envelopes radiating longer as they thin. Some decline cleanly, others pause on plateaus, flicker in day-scale jitters, or dip and recover as fresh physics enters the scene. Inside the outflow, structure blooms almost immediately. The burning does not deposit energy in a perfectly uniform way, and the accretion history has likely left asymmetries, a thicker belt near the equator, a preference for the poles in magnetic systems, or knotty clumps born of instabilities. Faster gas runs into slower gas and internal shocks form, moving boundaries where kinetic energy is turned into heat and the violent acceleration of particles. Those shocks are why novae sometimes speak in gamma rays and hard X-rays. Electrons, whipped to near-light speeds, spiral in magnetic fields and radiate. Protons colliding with other nuclei can spawn pions that quickly decay into gamma-ray photons. What once seemed a gentle optical lantern is, for a few days to weeks, a compact particle accelerator humming in the high-energy sky. As the shell expands, its density falls and its photosphere, where most of the visible light escapes, recedes in radius, even as the underlying white dwarf stays hot. The effective temperature climbs. In the ultraviolet, a forest of lines brightens and shifts, tracing the ionization ladder rung by rung. In soft X-rays, some novae enter a super-soft sourced phase. The residual nuclear burning on the dwarf's surface, now less shrouded by ejected gas, pours out photons in the tens to hundreds of electron volts, the whispery blue end of the spectrum. The timing of that soft X-ray emergence encodes the ejector's thinning. Its fade marks the end of sustained surface burning. While that blue flame lasts, radiative pressure can sit near the Eddington limit, the point where outward light pressure balances gravity for ionized gas, driving winds that further sculpt the shell. Chemistry threads through every step. The accreted skin is mostly hydrogen from the companion, but the nova's spectra often reveal heavier elements dredged up from the white dwarf's own outer layers via convection and mixing during the runaway. Dwarfs with carbon-oxygen cores seed the flow differently than those with oxygen-neon-magnesium cores, and that difference imprints abundance ratios. Neon-rich novae are telltales of ONE dwarfs. Ejecta masses are typically a few times 10 to the -5 to 10 to the -4 solar masses. Feather-like portions by stellar standards, but enough to carry clear chemical signatures when they thin into transparency. Those signatures matter to the galaxy writ large. Novae, multiplied over millennia, recycle and enrich the interstellar medium with specific isotopes and dust. Dust, the nova's capacity to make night glitter with smoke. Weeks after peak, as the outflow cools and the radiation field evolves, conditions in some novae allow carbonaceous or silicate grains to condense in pockets where temperature and density slip into the right corridor. When grains form, the optical light curve can sag, sometimes dramatically, as fresh, invisible soot absorbs and scatters starlight. Simultaneously, the infrared brightens as those grains re-emit what they've stolen as warm glow. Polarization can tick upward as scattered light becomes a larger fraction of what reaches us, signalling asymmetry in how the dust is laid down. Later, radiation and shock processing erode or reshape the grains, and the optical light recovers. Not all novae make dust. Those that do reveal a whole additional layer of physics as chemistry and radiation duel in an expanding, thinning medium. Behind the broad taxonomy, classical versus recurrent, stand clocks of accumulation. In recurrent novae, the white dwarf refuels and flashes again on human timescales, years to decades, because the accretion rate is high and the dwarf is massive, so less skin must be stored to reach runaway. In classical novae, the interval is centuries or longer. In both, mass is both gained via accretion and lost via rejection. Whether a white dwarf's mass creeps upward, downward, or stays roughly steady across cycles depends on details. What fraction of the accreted matter is actually retained, how mixing dredges core material into the envelope, and how violently the shell is thrown. This matters because a carbon-oxygen white dwarf that could somehow grow to near the Chandrasekhar limit, approximately 1.4 solar masses, becomes a candidate for a very different fate, a type WAST, a supernova. Most novae are not on that path. Many eject more than they store, and oxygen neon dwarfs are thought to avoid the IA route altogether. Still, the question remains an active, quietly debated thread. How much do nova contribute to the population of supernova progenitors, if at all? Viewed in radio light, the nova's breath tells a complementary story. Thermal free emission from ionized gas rises and falls as the outflow expands and recombines, encoding density and geometry. When non-thermal synchrotron appears, the shock's electron work is revealed directly. High-resolution radio imaging, months to years later, sometimes resolves lobes and rings, the fossilized shapes of flows that were once only line profile shoulders in a spectrum. In the infrared, fine structure lines from ions that prefer rarefied conditions paint the nebula phase as the ejecta settle into their long, fading afterlife. Geometry deserves its own quiet paragraph. The outflow is rarely a perfect sphere. An equatorial density enhancement, born from the disk-fed accretion, can produce a waste. Faster polar flows carve out dumbbell shapes, bipolar lobes whose edges first radiant as shocked skins, then cool into filigree. Inclination matters. Seen pole on, the shell may look like a ring, seen edge on, twin horns, at intermediate tilts, more like a bow tie. Polarization, line profile asymmetries, and, with time direct imaging collaborate to reveal the three-dimensional shape. The fact that this sculpting emerges from a runaway only meters thick at ignition is one of those satisfying astrophysical reminders. Tiny beginnings lead to grand, legible forms. The companion's role never really ends. In some systems, it is a main sequence star quietly losing a whisper of atmosphere. In others, a bloated red giant whose wind already fills the region with slow-moving material. When the runaway's outflow slams into that pre-existing wind, shocks are stronger, gamma rays brighter, and radiosynchrotron more likely, an external target for a newly launched bullet. In yet others, the white dwarf's magnetic choreography modulates the way matter lands, leaving signatures at specific rotation periods in brightness and line shapes, a celestial heartbeat folded into the nova's broader pulse. All of this sits on a lattice of numbers that are, in themselves, soothing to hold. Surface gravity is near 10 to the power of 8 to 10 to the power of 9 centimeters per second squared. Ejection velocities from a few hundred to several thousand kilometers per second. Ejected masses around 10 to the minus 5 to 10 to the minus 4 solar. Peak luminosities climbing toward, and sometimes brushing, the Eddington limit for a sun's mass. Soft X-ray phases that last weeks to months, switching on when the ejector thinned to transparency, column densities dropping below approximately 10 to the 21st power centimeters to the negative second power, and switching off when the nuclear flame finally gutters. Decline times whose histograms are as variegated as the systems that produce them. Each number tucks into place beside the last until the runaway, once a blur, becomes a sequence your mind can walk through slowly. From a backyard or a mountaintop, the translation from physics to experience is wonderfully direct. A white dwarf quietly cannibalizes a little hydrogen through the L1 spillway of a companion. The layer thickens, heat rises, and, because degenerate matter is stubborn, the thermostat fails. Fusion runs away, a thin skin explodes outward, the system brightens, lines go broad, then narrower, then split. The continuum hardens from visual to UV to soft X-ray, then softens again when the flame is out. Radio murmurs, infrared glows, sometimes dusk grows and makes a brief night within the night. Weeks pass, the shell keeps flying, the binary settles back to quiescence, the disk rebuilds, and, on timescales that might be months or centuries, the hourglass at L1 begins to fill again. There is room, even within such an efficient chain of cause and effect, for surprise. Some novae oscillate on the way down from peak, stepping down in a stare of small rebrightenings. Some produce transient jets, a brief flirtation with collimated outflow. Some show extraordinarily early dust formation, as if chemistry somehow outran the expected cooling curve. A few reveal neon in emphatic tones. Others seem parsimonious with heavy elements, reminding us that mixing is not guaranteed. And though convergence is strong, novae rhyme. Across decades and constellations, each one pronounces certain syllables more clearly than others. That individuality is why telescopes slew night after night to follow the decline, why radio arrays return weeks later, why ultraviolet spectrographs make time mid-orbit, and why, on the smallest porches and in the largest domes, people keep setting alarms for the hour when Centaurus or Sagittarius clears the trees. If you place this gentle explosion alongside the other threads that preoccupy us, solar storms, earthquakes, and a passing interstellar wanderer like 3i Atlas, the scales separate themselves. A nova is distant and safe, its photons left when ancient rivers still chose their beds. Its high-energy murmur is a message, not a threat. Yet as a teaching instrument it is exact. It shows how gravity, quantum mechanics, thermonuclear fusion and radiation pressure and fluid instabilities can combine in a few square meters of fuel to write a visible mark across half a galaxy. It shows how a quiet trickle through L, one can, without sound or smoke, lay the groundwork for a lantern in the Milky Way. And it shows how the universe, even in its gentlest explosions, keeps time with clocks that are both sudden and patient, both violent and controlled, both simple to describe and endlessly satisfying to watch. The first pulse is so small that only instruments notice it. Far from Zulia, needles quiver on paper, accelerometers wake, GPS receivers begin recording motions too slight for human ankles to feel. A few seconds later, the faster compressional waves, the P waves, arrive in towns and farms. A subtle, almost unnameable pressure that makes dishes tick and doors whisper against their frames. Then the shear waves come side to side, and the difference is written across kitchens, offices, and plazas. Hanging lights swing, dogs bark. People look up as if the room had just remembered it was attached to the ground. At 22:21 UTC on September 24th, a fault segment east-northeast of Mene Grande slips at a depth of only a handful of kilometers. That shallowness makes all the difference. With little crust above to dilute them, seismic waves retain their sharpness, carrying strong accelerations into the surface layers where buildings sit. In one apartment, a glass of water sloshes rhythmically. In another, a closet door slides open, and the sound it makes, rollers crossing a seam, imprints itself in memory. The motion lasts longer than people expect. Not the snap of a thunderclap, but a drawn-out conversation between the Earth's elastic layers and the structures we have anchored to them. Magnitude is the word that makes the headlines, but intensity is the word your body understands. Magnitude measures the total energy released at the source. Intensity tells how hard it shook where you were. Two places the same distance from the epicenter can feel the event differently depending on what's underfoot. Soft, water-saturated sediments amplify certain frequencies, like a bowl that prefers to ring at one tone. Hard rock damps them. Around Lake Maracaibo, the basin's layered sediments behave like a giant amplifier at some locations and a muffler at others. That is why in one neighborhood a child rolls over and goes back to sleep, while in another kitchen a pot rattles toward the edge of a stove. On the instruments the signatures are clean. The first arrivals mark out the distance. Later phases, waves that have bounced, bent and threaded their way around discontinuities, fill in the Earth's story between source and station. Strong motion sensors record peak ground acceleration and velocity, the quantities engineers feed into design curves. Spectral accelerations at 1 second, at 2 seconds, at short periods, numbers that translate directly into the demands placed on low-rise masonry, flexible mid-rises, and tall, lightly damped towers. When civil engineers look at the plots, they don't see a jolt. They see a set of demands distributed across frequencies, and they ask whether the buildings in Zulia were tuned to meet them. The fault that moved is part of a tangled boundary. To the north, the Caribbean plate shuffles eastward relative to the South American plate, and the pressure between them is resolved by a network. Strike-slip segments where blocks slide past each other laterally, thrusts where one rides up over the other, and oblique combinations where reality ignores our neat categories. Names drawn on maps, Bocono, Oca Ancon, Santa Marta, Bucaramanga, are ways to keep track of behaviours that twist and merge at depth. In this region, right lateral motion, imagine standing on one side of a fault and watching the other side move to your right, is common. The focal mechanism, those beach ball diagrams seismologists love, will later show which plane slipped and which direction the first motion took. When the first rupture ends, the crust is not done rearranging itself. Stress doesn't vanish, it redistributes. Some nearby patches of fault feel a little safer, others a little closer to failure. Hours later, at 0351 UTC on September the 25th, another segment yields at roughly twice the depth of the first. To the people on the surface, the effect is unsettlingly similar. Prolonged swaying, doors banging in their frames, the soft percussion of small objects finding new positions. To the instruments, the second event is distinct. A deeper origin, a slightly different balance of high and low frequencies. A waveform that tells of a source a few kilometers farther down where temperatures and pressures nudge rocks toward different behaviors. Magnitudes can differ by tenths. On a logarithmic scale, that still means a noticeable change in energy. It isn't simply another quake. It is the Earth redrawing stress lines where the first rupture left them sketched. As the pair settles into the record, the aftershocks begin to trace the hidden geometry. Omori's law, Aftershocks decay approximately inversely with time, shows up like clockwork. Many small events in the first hours, fewer, still smaller in the first day, a tapering that will continue for weeks. On a map, the aftershocks do not land randomly. They cluster along the ruptured fault and at its edges, lighting up the edges of the slip patch, finding places where the main shock brought faults closer to their thresholds. If you could see the Coulomb stress changes, the way the first events added or subtracted the kind of stress that promotes failure, you would see a pattern of red and blue lobes draped across the fault network. The aftershocks, in their own language, are drawing that pattern for you. Inside buildings, the way things move can be translated back to numbers. A person on the 6th floor felt a slow rolling motion that made walking as strange as carrying a full bowl across a moving train. A person on the 1st floor felt a sharp jolt and heard a low hum into the walls. That's higher mode amplification. A tall building behaves partly like a guitar string with multiple harmonics, each with its own resonant period. If the ground motion's dominant periods matched a building's natural periods, the amplification was strong. If they missed, the motion felt oddly gentle for the magnitude. Engineers reconstruct this match or mismatch after the fact with response spectra, curves that show the maximum response of perfectly tuned oscillators at each period. A bump in that spectrum near, say, 0.3 seconds might spell trouble for unreinforced masonry. A bump near 2 seconds might have unsettled taller frames. Across Zulia and into Columbia, emergency protocols unspool. Elevators are stopped and cleared. Hospitals run through checklists designed exactly for moments like this. Oxygen lines, generators, surgical lights. Bridges are inspected first by eye and then with instruments. Dams and levees are checked for settlement and seepage. In homes, gas lines are sniffed, then shut if anything seems odd, a habit that saves lives. People gather in open spaces and feel the relief that comes from being under nothing but sky. Back at the maps, agencies publish slightly different magnitudes and depths for the same ruptures. To a non-specialist, the variation feels like disagreement. To a seismologist, it is the natural result of different data sets, different filters, different definitions of magnitude. Moment magnitude, MW, is tied to the total energy and fault area. Body wave MB and surface wave MS magnitude is key off specific parts of the waveform and can saturate for big events. Early numbers often update as more stations report and inversions refine. Depth is the trickiest piece. With sparse station coverage in one direction or noisy arrivals, a best fit depth can wander by several kilometres. Even the epicenter, the mapped point on the surface, can migrate a few kilometres as data improves. No prediction algorithm clicks into place. There are no reliable short-term precursors to tell you which small foreshock belongs to a larger event and which is only an aftershock of a quake that will never come. There are statistical statements though, and they are useful precisely because they're modest. After a main shock, the likelihood of another event of similar size rises temporarily. That probability decays with time, and in most sequences the largest event has already happened. Increased but still small is not comforting phrasing, but it is honest, and honesty keeps communities from either panic or complacency. Preparedness drills, building codes and retrofits are the tools that work. Calendars and rumour do not. In the days that follow, satellites add another layer of measurement. Interferometric radar in SAR compares the phase of radar reflections from before and after the earthquakes and turns the differences into a fringe map of ground deformation. Each coloured band is a sliver of motion toward or away from the satellite, and together they outline the bulge on one side of the fault and the drop on the other. GPS stations show millimetre to centimetre offsets. With these, seismologists invert for a finite fault model. The patch of crust that slipped, how much it slipped at each point, and in what direction. It becomes possible to say not only how much energy was released, but exactly where, as if a blindfold had been removed from the fault. For residents, the maps are less compelling than a single tangible question. What about the next one? The answer returns to ground conditions and structures. On soft soils, mid-rise buildings with poor lateral resistance are vulnerable. On firm ground, heavy unreinforced walls and parapets are the things to worry about. Retrofitting can be as humble as adding proper ties to walls and roofs, securing water tanks and chimneys, bracing tall shelving, or as sophisticated as installing steel frames, adding shear walls, or base isolation in critical facilities. The language of risk shifts from if to how much and where, which is a better register for making decisions at kitchen tables and city halls. The twin earthquakes are part of a story that runs on 2 clocks at once. On human time, they are sudden and dramatic. On geological time, they are inevitable and spaced by long, quiet intervals of stress accumulation measured in millimeters per year. Plate motions on the order of a few centimeters per year seem trivial until you multiply by decades. Suddenly, years of silence contain the energy for a minute of motion that people will talk about for the rest of their lives. That is the essence of elastic rebound. Strain stored elastically in rocks until strength gives way, then released, then stored again. Reports arrive of lights in the sky, of animals acting strangely, of wells rising or falling. Some of these have simple explanations. Transformers shorting out during shaking make blue-green glows on the horizon. Pets react to the behavior of humans and to unusual motion in the floor. Water levels can change when fractures and aquifers open or close. Scientists are cautious with such reports, curious, respectful, and disciplined about separating what is plausible from what is compelling. It's easy to stitch omens after the fact into a narrative that feels predictive. It's harder and more useful to let data decide. Communication matters as much as measurement. In the press conference room, a geophysicist draws a rectangle on a map to show the likely slipped area and says plainly that aftershocks will continue, that most will be small, and that a handful may be felt. They remind people to check shelves and gas lines, to keep heavy objects low, to sleep away from tall bookcases for a few nights, to carry a flashlight by the bed. The calm tone is not an act. It's a trained response. The same one used whether the week also contains bright novae, active solar weather, or the slow approach of something like 3-eye Atlas. The Earth, the Sun and the stars keep their own schedules. Our job is to know the schedules well enough to live with them. In classrooms and on job sites, the events become lessons immediately. Students plot aftershock decay and see Amori's law emerge from messy data. Engineers fold the recorded response spectra into site-specific hazard curves and ask whether older buildings in lake sediments meet modern drift limits. City officials review the locations of shelters relative to bridges and overpasses and ask whether signage and lighting are sufficient for nighttime evacuations. The week's other dramas, space weather models, telescope repointings, citizens stepping outside to find a new star, run in parallel. Each thread has its own vocabulary, its own instruments, and its own cautions and delights. It is the proximity and time that makes them feel braided, not a shared cause beneath. A person in Maracaibo tells a friend by voice note, "I never felt the floor move like that." The friend replies with a video of a chandelier drawing neat ellipses in the air. A shopkeeper posts a photo of hairline cracks that trace the weak points in plaster and vows to fix the shelves that toppled. A civil engineer in a pickup traces a route across bridges, feeling with trained hands for joints that did not settle cleanly. A night shift nurse says the beeping in the ward briefly took on a different rhythm and then returned to normal, and in the quiet after, the small noises of machines sounded like reassurance. The paired events will be logged compared with twins elsewhere in the world and folded into regional hazard models. They will sharpen estimates of which segments are loaded and which are, for now, relaxed. They will provide new ground motions to calibrate simulations against. They will leave behind small telling changes in the way doors hang and the way people talk about where they were when the ground decided to move. They will not, by themselves, predict the next large earthquake. They will remind everyone that the right answers come from steady preparation and a patient attention to the stubborn physics of plates and faults and time. Clusters begin with a simple fact about rocks. They do not fail smoothly. Stress accumulates for years along rough, locked patches of a fault, asperities, until one patch can no longer hold. It breaks, and that break changes the stress felt by neighbouring patches. Some are relieved and become quieter for a while, others are nudged closer to their own thresholds. The result is not a single isolated earthquake, but a sequence, a main shock, a cascade of aftershocks, sometimes a second main shock on an adjacent patch, sometimes a chain of events that wanders along the fault like a zipper, being tugged open in uneven pulls. If you lay the times of the aftershocks on a line and count them up, a pattern emerges quickly. Many arrive in the first hours, fewer the next day, fewer still the day after that. Omori's law, later refined by Utsu, captures this decline with a simple formula. The rate of aftershocks decays roughly as 1 over time plus a constant, a smooth slide from frantic to sparse. The elegance of that curve is that it doesn't require you to know the detailed geometry underground. It falls out of how stress redistributes and how faults with rate and state friction respond. In rate and state language, a sudden change in stress transiently increases the slip rate on nearby patches. That extra seismicity rate relaxes back toward background as the state variable, a memory of contact conditions on the fault, evolves. Alongside the timing sits the size distribution. Whether you are counting aftershocks in Zulia or in Japan, you'll see many small events and progressively fewer large ones. And the relationship follows the Gutenberg-Richter law. The number of earthquakes larger than magnitude M drops by a factor of about 10 for each unit increase in M. The slope of that drop, the B value, hovers near 1 in many regions but shifts with faulting style and stress conditions. Under higher differential stress, B can dip. Under lower stress or in volcanic areas, it can rise. Watch B values carefully during a sequence, and you may see hints of how the crust is loading and relaxing, though the signal is subtle and noisy. Another empirical pattern rides quietly beneath the headlines: Barth's law. On average, the largest aftershock in a sequence tends to be about 1.2 magnitude units smaller than the main shock, regardless of how big that main shock was. The law doesn't tell you which aftershock it will be, or when it will occur, only that the statistical drop is stubbornly consistent. For emergency planning this matters. If a magnitude 6.3 ruptures, planning for the possibility of a high 5 aftershock is prudent, and that prudence fits hand in glove with Omori's decay. The earliest days are the ripest for that largest follower. All of this sits on two ways stress from one earthquake reaches another: static and dynamic triggering. Static stress changes are permanent rearrangements, Coulomb stress transfer, caused by the way a slipped patch relieves stress in one lobe and adds it in another. If your patch of fault falls in a red lobe, your failure clock may jump forward by days to years. If it falls in a blue lobe, it may be pushed back. These static changes fade with distance but can be decisive within the same fault system. Dynamic triggering rides the seismic waves themselves. As the main shock's waves pass, they jiggle faults far afield, modulating pore pressures and frictional strength for seconds to minutes. Occasionally, in critically stressed fluid-rich areas, that fleeting encouragement is enough to start a local sequence, an earthquake swarm that begins right as the waves pass and continues for hours. Dynamic triggering is flashy but rarely loads big guns by itself. Static changes are the quieter architect of most local clustering. Not every cluster has a clear main shock. Swarms, common in volcanic and geothermal regions, can unfold as dozens to hundreds of similar magnitude events over days to weeks, migrating in space like a slow luminous worm on a map. In swarms, fluids and heat often matter. As hot water and gases move through fractured rock, they change effective normal stress on small faults by altering pore pressure. Push a little fluid into the cracks and the weight pressing the two sides together relaxes, making slip easier. Diffusion of that pressure front can leave a signature, a spreading ring of activity that grows as the square root of time. In tectonic settings without heat or magma, swarms can still appear where fluids are abundant, within sedimentary basins, near large reservoirs after impoundment, or near injection wells. reminding us that the crust is not a dry stack of bricks but a porous, leaky sponge. Where the ground shook in Zulia, the cluster that followed the paired events traces the edges of the slipped patches like a weather radar image outlining the gust front after a storm. The first rupture unloaded stress on its own patch but lobed extra stress onto neighbours. Hours later, a deeper patch failed, reshaping the stress field again. Aftershocks then filled in the outline, tighter near the patch edges, sparser in the quieted interior, a few outliers lining up along small splays and stepovers. If you could see stress, you'd see a lacework of plus and minus draped over an already complex network of strands. The aftershocks are the crayons the Earth uses to colour that lacework for us. The friction that governs these slips is not uniform sandpaper. Rate and state friction says that the resistance a fault offers depends on how fast it is sliding, and on a slowly evolving internal variable that remembers how long the tiny contact junctions, asperities, have been aging. Hold two rough surfaces together quietly, and microscopic welds grow stronger. Start them sliding and they weaken until a new dynamic balance is found. That dependence on sliding rate and contact state is why small stress increases cause bursts of activity that then relax, and why seismicity can be so sensitive to tiny perturbations when a fault is near criticality. Sensitive does not mean omnivorous. Many proposed triggers leave little or no footprint in the data. Tidal forces from the moon and sun do measurably modulate seismicity in some settings, particularly for very shallow or tidal phase sensitive systems, but the effect is small. Weather-driven surface pressure changes can be recorded by instruments, but typically fall far short of the necessary stress change to matter for all but the touchiest faults. Space weather, the dance of currents in the ionosphere and magnetosphere, produces electromagnetic variations that instruments register cleanly, but their coupling into the crust is weak. Whatever patterns human minds attempted to trace across the sky and into the ground, the stubborn lesson of catalogues is that plates and faults respond mainly to the slow push of tectonics, the quick redistributions of nearby ruptures, and, in special cases, to the movement of fluids. If you want to forecast, not predict, but forecast, how a cluster will behave, you reach for simple, transparent tools. The ETAS model, epidemic-type aftershock sequence, treats each earthquake as a parent that spawns its own children according to Amori's time, decay and Gutenberg Richter sizes, and each child can be a parent in turn. It's a branching process with parameters tuned to local catalogues, a productivity that says how many aftershocks of a given magnitude typically spawns, an Omori p-value that controls how fast the sequence quiets, a b-value that sets the size distribution. Feed ETAS the main shocks and the early aftershocks, and it will give you probabilistic rates. How many events above magnitude 4 to expect tomorrow, next week, next month. These rates aren't prophecies, they are odds that help agencies stage resources and help the public calibrate caution. In parallel, static stress models compute Coulomb stress change on mapped faults. If a segment to the northeast lit up red, stress increased by, say, a few tenths of a bar, that segment's near-term probability of slipping rises relative to background. A few tenths of a bar may sound small, but crustal rocks at failure are exquisitely sensitive. Adding or subtracting the equivalent of the weight of a parked car per square meter can matter when you're at the edge. These stress maps do not decree the next rupture. They identify where the dice are now a little more loaded. Clusters also reflect the segmentation of faults, the way barriers, bends, and stepovers break a long fault into sections that can fail together or separately. A bend that forces a fault to compress a little will often arrest a rupture. A releasing bend where the geometry opens space can encourage slip to jump across a gap. In a cluster, you can sometimes watch a rupture, front die at a compressional stepover, and then, days later, see a neighbouring segment fail in its own right, as if the earlier slip had quietly thinned the wall between rooms, and only later did the next door swing open. Beneath the brittle lid where earthquakes nucleate, the deeper crust flows slowly on timescales of months to years. After a large earthquake, That warmer, ductile layer can ooze in response to change stresses, a process called viscoelastic relaxation. As it does, stress in the brittle lid evolves again, subtly loading and unloading patches over months. In some sequences, a second burst of aftershocks months later can be traced not to any immediate nearby rupture, but to this deeper, slower adjustment. The cluster, in that sense, has a long tail that extends beyond what felt urgent in the first week. Fluid movement adds another long tail. When a big rupture changes stresses, it also changes pore pressures by squeezing and dilating the rock. Those pressure changes diffuse through cracks and pores over weeks to months. Where diffusion travels into a critically stressed patch, a new swarm can blossom independent of static stress lobes. In places with active hydrocarbon extraction or wastewater disposal, human activity can superimpose its own pressure changes on the natural field, creating clusters that mimic tectonic ones but are ultimately tied to injection schedules and reservoir volumes rather than to plate motion. Disentangling natural and induced clusters is now a steady job for regional networks. For engineers, clusters are less about metaphysics and more about sequencing risk. After a main shock, they know that the largest aftershock, if it comes, is most likely in the first days. They schedule detailed inspections of critical lifelines immediately. Hospitals, bridges, power substations, water plants. They expect many small aftershocks. They expect a few moderate ones. They make sure temporary shoring and red tagging protocols account for repeated shaking. Retrofit priorities lean into what the recorded ground motions say, not just what the magnitudes suggest. If the spectrum was rich in 1 to 2 second energy, mid-rise frames are looked at with extra care. If a short period peaks dominated, unreinforced masonry gets urgent attention. For those who live on these faults, clusters teach habits. Keep heavy items low and secured, know where the gas shutoff is, sleep a little farther from tall shelves in the first nights. When an aftershock wakes you, note, shorter and sharper than the main shock, longer and rolling, farther away. These are human scales of observation that later line up with maps and numbers. You do not need to compute a Moore's law in your head to know that the long tail of small events is part of the Earth's quieting, and that the odds of another large one fall with each uneventful day. It is tempting, in a week crowded with névé, solar storms and the measure glide of 3i Atlas, to see clustering everywhere and to assume some grand baton is conducting sky and ground. The discipline that keeps seismologists sane and keeps communities safe is the willingness to let each domain keep its own physics. Faults cluster because stress transfers, friction is state-dependent, fluids move, and the deep crust relaxes. Those ingredients are enough. They are also intricate and beautiful on their own, rich enough to fill a lifetime of quiet watches and careful notebooks without help from distant fireworks. When the sequence finally thins to a whisper, the fault has not healed. It has only settled into a new arrangement of stress and strength. The clock that counts toward the next break starts again, not from zero, not from fate, but from millimeters per year of motion, from grain-on-grain contact aging at depth, from tiny chemical welds forming across dark surfaces. Clusters are how the crust exhales after holding its breath too long. Understanding their shape, time decay, size distribution, stress maps, swarms and sequences lets us turn worry into work. Inspections, retrofits, drills, and the quiet knowledge that shaking arranged in bursts is not a universe out of order, but a planet practicing the only arithmetic of motion it has ever known. The sun wears its moods on its surface. When it's calm, you can mistake it for a simple lamp, steady, unchanging, politely bright. Near its peak, you begin to see its true character, a magnetic engine with tangled thoughts, working them out in loops and arcs, and sudden exhalations that cross the whole span from wisp to roar. The cycle behind that mood, the roughly 11-year rise and fall of activity, comes from the slow flip of the sun's global magnetic field. Every maximum is the moment when the field is most knotted close to the surface, when the orderly bar magnet of solar minimum has frayed into archipelagos of north and south scattered across the photosphere. Where those opposite polarities butt heads, sunspots appear. Dark islands, cooler than their surroundings because magnetic fields there have bottled up convection. The number of spots is a crude but useful calendar. More spots, more chances for stress to build and release. More loops, more opportunities for reconnection. More reconnection, more flares and coronal mass ejections. A sunspot is not a hole. It is a place where magnetic field lines pierce the surface in a bundle so strong, thousands of Gauss, that the normal bubbling of hot plasma is suppressed. Around each spot, in magnetograms that map polarity like a weather chart, you can trace magnetic neutral lines where the sign flips. Along those lines, shearing flows and differential rotation wind the field like taffy. The field resists twisting for a time, storing energy as tension in its geometry. Then, somewhere in the invisible three-dimensional lattice above the spot group, the field rearranges in a sudden act of topological mercy. Magnetic reconnection. In a flare, that reconnection happens in a compact volume and disgorges energy as X-rays and extreme ultraviolet light in seconds to minutes, light that runs ahead of any particles or plasma and hits the top of Earth's atmosphere 8 minutes later. In a coronal mass ejection, reconnection opens a gate on a much larger structure, and an entire bubble of magnetized plasma lifts off and goes. The texture of that going is its own quiet satisfaction. In white light coronagraphs that occult the sun so the faint corona can be seen, a classic eruption shows a three-part structure: a bright front where swept-up coronal plasma piles, a dark cavity that marks a flux rope, twisted magnetic field wound like a rope, and a brighter core, often filament material from lower layers that the field pulled along for the ride. Viewed edge-on, some look like tangled smoke rings. Viewed head-on, they look like halos, rings that expand until they seem to enclose the sun. Those halo CMEs are the ones with the greatest chance of intersecting Earth, because the ring is the face of the bubble coming more or less toward or away from us. Speed matters. A slow CME a few hundred kilometers per second ambles through the ambient solar wind and will arrive days later, gentler, sometimes merging with other structures. A fast CME over 1,000 kilometers per second drives a shock ahead of it, like a ship making a bow wave, accelerating particles along the way. Those solar energetic particles can reach the polar caps quickly, hours before the bulk plasma arrives, sprinkling the upper atmosphere with extra ionization, and occasionally even lighting up neutron monitors at ground level, in rare ground level enhancements. The bulk structure, the interplanetary CME, will reach the Earth in 1 to 4 days, depending on launch speed and the low, patient tug of drag in interplanetary space. Forecasting that journey as a craft half fluid dynamics and half magnetism, models that begin at the sun's surface, where maps of the magnetic field are stitched together from daily observations, feed into coronal solutions that estimate where the solar wind flows fast and slow, and then into heliospheric models that can carry a CME outward as a blob embedded in a moving river. The details are chewy. Choose a background wind that matches what spacecraft see, nudge the CME's launch direction and width and speed until synthetic coronagraphs resemble real ones. Then watch how the blob distorts over distance as it plows through slow wind or gets buffeted by fast streams. Even the best of these models cannot tell you the CME's internal magnetic field at arrival, because that field is the entire point. It is what you are trying to know. So the forecast often comes with careful words, a predicted arrival window, a speed range, and a reminder that the most important number of all, the orientation of the field when it arrives, can only be measured at the last moment by sentries parked upstream from Earth. Those sentries live near the first Lagrange point, a perch 1.5 million kilometers sunward, where spacecraft like DSCO-VR and AC sip the solar wind and send the taste back home in real time. They measure velocity, density, temperature, and the magnetic field vector. The field's north-south component, called BZ in GSM coordinates, is the hinge on which the door to Earth's magnetic shield swings. If BZ points northward when the structure arrives, aligned with Earth's dayside field, coupling is weak and much of the storm's energy glances off. If B's turns southward, opposite to Earth's dayside field, reconnection can run efficiently at the magnetopores, threading solar wind field lines into Earth's system and opening a conduit for energy and plasma to pour in. A storm that looked modest can deepen if BZ tips south and stays there for hours. A storm that looked fierce can fizzle if B's stubbornly holds north. When coupling is strong, Earth's magnetosphere deforms and breathes. The dayside magnetopause is pressed inward. On the night side, the magnetotail stretches and stores energy until reconnection there lets it snap back, flinging plasma earthward along magnetic field lines. At high latitudes, the auroral ovals brighten and swell equatorward. The ionosphere, those D, E and F layers that radio operators know like old friends, changes character as energy and particles rain in. In the D layer, increased ionization during strong X-ray flares and solar proton events can absorb high-frequency radio like a sponge, creating radio blackouts on the dayside. In the F layer, storm time composition changes and travelling disturbances can distort and delay GPS signals. The storm, from Earth's point of view, is both a light show and a reconfiguration of the planet's great thin conductive skin. There are tidy indices for all this. Kp, a quasi-logarithmic measure of global magnetic disturbance, ticks upward as magnetometers around the world agree that unusual has become common. DST, the disturbance storm time index, goes negative as the storm time ring current grows, a donut of energetic ions trapped around Earth that deepens the magnetic field at mid-latitudes. AE indices track the quick convulsions of substorms in the auroral electrojets. Operational space weather groups wrap these into scales. G for geomagnetic storms, from G1 to G5, R for radio blackouts tied to X-ray flare class from R1 to R5, S for solar radiation storms, rated S1 to S5 based on particle fluxes. The scales are less poetry than planning tools, ways for airlines, power grid operators, and satellite controllers to know when to enact procedures that move risk from the realm of surprise into the realm of routine. Power systems care about what the storm does to the ground. When the magnetosphere shakes, it induces electric fields in Earth that drive currents along long conductors at the surface, power lines, pipelines, rails. These geomagnetically induced currents prefer the path of least resistance, wandering in through transformer neutrals and saturating cores designed for a steady diet of 50 or 60 hertz. In a mild storm, this is noise. In a severe storm, it is heat and protection trips and very occasionally hardware damage if precautions are not taken. Grid operators answer with vigilance, monitor harmonics and reactive power, redistribute loads, temporarily reduce transfers, and when necessary take vulnerable components offline for the peak of the storm. Spacecraft feel the storm from above. The thermosphere warms and puffs up as energy from the magnetosphere and ionosphere trickles downward. At low Earth orbit, that means more drag. Satellites drop a little in altitude. Constellations drift from pre-planned spacing, and operators fire thrusters to keep formations square. Surface charging and deep dielectric charging, electrons piling onto and into a satellite, can lead to tiny arcs and upsets. Single event upsets in electronics become more likely when a particle fluxes are elevated. None of this is insurmountable. All of it prefers a heads up with hours of lead time and a slow, practiced hand on the controls. If you want to watch the sun behave, you do it at many wavelengths. In extreme ultraviolet, the Solar Dynamics Observatory shows the corona as if it were lace made of fire, loops bright in particular channels that isolate million-degree plasma of different flavours. In white light with a coronagraph, you see the slow kingdom beyond the limb, streamers leaning in the slow solar wind and plumes roaring in coronal holes where open field lines let fast wind escape. In vector magnetograms, you see the photospheric field like iron filings but with numbers, and you can compute where the free energy over and above the potential field, has piled up. Parker Solar Probe and Solar Orbiter fly into the wind itself, threading between the Sun and Earth to feel structure before we do. The stereo view of near-Sun space turns a guess about whether a CME is headed our way into a measured geometry. It is tempting to file all of this under spectacle, but it is better to file it under weather. Predictable in flavour, emergent in detail, most dangerous when ignored. Flares are classified by their peak soft X-ray flux, C, M, X, each 10 times the previous, with a number as a multiplier. An X2 is twice the peak of an X1. Flare photons make their mischief on the day side almost instantly. Radio absorption increases in the D layer. The ionosphere ripples. GPS and HF operators see it as if someone breathed on their signals. Solar radiation storms, S1 to S5, unfold over hours as particles accelerated near the Sun or at interplanetary shocks arrive. They matter most for high-latitude flights and for people and instruments above the protection of atmosphere and field. Geomagnetic storms arrive last, with their hours to days-long choreography of magnetopause erosion, ring current build-up and auroral electrojet convulsions. The seasons have their say. Around the equinoxes, geometry conspires with the interplanetary magnetic field to ease reconnection on Earth's dayside, a pattern called the Russell-McFerrin effect. It is not that the Sun is angrier in September and March, it is that Earth is more receptive to the Sun's normal moods. A modest southward buzzy in the solar wind can couple a little more efficiently to the magnetosphere, and a storm that would otherwise be a shrug becomes a postcard glow over latitudes not used to aurora. The same geometry also mutters in the ionosphere. Conductivity patterns change, winds aloft shift, travelling ionospheric disturbances ride along like ripples in a lake after a motorboat has passed. Inside this weather, small narratives unfold at human pace. A pilot on a polar route checks messages and sees HF degraded, and takes a more southerly track that costs a little fuel and gains a lot of margin. A power control room in a high-latitude grid sees reactive power demand climb and calls up a plan already written on a laminated card. Shunt capacitors are adjusted, non-essential maintenance is deferred. Operators settle in for a long, alert shift. In a small observatory, someone watches an all-sky camera pick up a faint green arc that grew from nothing an hour ago, and whispers in a dark room so as not to break the spell. Somewhere else, a student downloads magnetometer data from a backyard induction coil and sees the storm as a wobble on a line that before tonight seemed more like homework than like the pulse of a planet breathing under space. The word maximum can mislead. It suggests a peak you reach and descend from immediately. In practice, solar maxima are plateaus with steps. Activity waxes, wanes and waxes again over months as the Sun's northern and southern hemispheres take turns being exuberant. The global polarity reversal, the flip that marks the true mid-cycle moment, can lag in one hemisphere and lead in the other, making a messy map that only a patient mind can love. From Earth's vantage point, that messiness is kind. It spaces out the most intense episodes so that our responses can be thoughtful rather than frantic. Because the Sun's cycle is slow, it acts as the key signature for whatever else we are trying to pay attention to. If the story this week includes earthquakes and novae and the long glide of something like 3i Atlas, the solar maximum is simply the background against which a particular kind of interaction becomes more likely. When a coronal mass ejection sweeps across an ordinary comet, we have seen tails severed cleanly and then regrown, magnetic reconnection written in visible ink. When the same kind of structure encounters an interstellar visitor, our curiosity wakes not because the physics is different, but because the composition and history of the target are new. Magnetic flux ropes and sheaths and shocks do what they always do. The question is what a nucleus forged in another stellar nursery will show us about how it receives the Sun's breath. If you sit with the Sun long enough, browse its magnetograms as if they were a daily shoreline, compare today's coronal holes to last week's, thread the whisper of L1 readings into your afternoon, you start to hear its grammar. Emerging flux is a preposition connecting what is below to what is above. Shear is an adjective, loading the sentence with tension. Reconnection is a verb clearing the syntax with a clause that resets the sentence. CMEs are long, rolling dependent clauses that take a paragraph to complete, and flares are exclamations that need no explanation. The magnetosphere is the reader, sometimes receptive, sometimes resistant, sometimes tired, and sometimes limber. In a week like this one, full of other voices, the sun still gets a chapter to itself, not because it shouts, but because its weather runs under everything else like a tide, steady and patient, reshaping shorelines while we sleep. It began as a smudge that moved when the rest of the sky held still. Survey cameras were sweeping their grids the way they always do. Same cadence, same sky cells, same habit of noticing the almost nothing, and in a few frames spread across a quiet pre-dawn, the almost nothing shifted just enough to ask for a second look. The software flagged it. A human checked. The next night, more frames landed with the same patient drift against the star field. Submit the astrometry. Wait for orbit solvers to give a first guess. The first guess came back with a jolt of strangeness baked in. The path was not closed. The residuals tightened as more positions arrived. The covariance shrank, and the solution held its ground. Hyperbolic, retrograde, dropping in from high above the planetary lanes and aiming to slice through the ecliptic rather than skim past it. There is a special quiet in the moment when a catalogue number becomes a sentence. Third of its kind, not a native, not bound. It will not loop back on schedule and give us another try. 3i Atlas, the name holds both the count and the gratitude to the survey that caught it, an acknowledgement that a plain, all-sky habit of watching is how these shy travellers are found. From that first orbit fit, the geometry wrote itself like a map unrolling. A high inclination, almost upside-down approach relative to the planet's forward spin. An eccentricity comfortably greater than 1, the mathematical way of saying this is passing through. A hyperbolic excess speed, the speed it will take with it back to interstellar space, measured in tens of kilometres per second, enough to cross the inner solar system in months, not years. Not a sprint, not a dawdle, a glide that would put it near Mars in early October, closest to the Sun by late October, and nearest to Earth, still properly distant, in December. In the first hours after the solution firmed, observatories large and small did something that always feels like a small miracle. They turned, almost as if one instrument. On a screen in a control room it is not much, a fuzzy star at the limit of a short exposure. An hour later, the fuzzy star is not where it was. Plate solve, subtract the background, stack frames along the object's motion vector, and the smudge resolves into a bead with a faint haze around it. That haze is the coma, the first breath of gases released from ices warmed above their long interstellar sleep. The coma is a laboratory we can work with from absurd distances. Spectrographs split its light into razor-thin rainbows and let familiar fingerprints step forward. The violet band of CN, the swan bands of C2, NH2, and OI, when the conditions are good, CO and CO2, in the infrared when instruments can look that way. From the strengths and ratios of those lines, we can back out production rates, how many molecules per second are boiling off, and then, with a little more modelling, infer something about the interior stock of ices and the grains hitching a ride in the flow. Brightness becomes a conversation rather than a number. Native asteroids obey a tidy law: distance to Sun, distance to Earth, a phase function, and their light curves behave like clock hands. Active comets and visitors like this are creatures of habit and surprise. The usual approximation writes the total magnitude as a heliocentric power law, r to the power of negative n, with n somewhere between 2 and 5 depending on how vigorously the surface responds to sunlight. But surface may be too simple a word. Activity is patchy. jets turn on and off, and the subsolar latitude swings as the nucleus rotates and the geometry shifts. The quantity that observers pass around like a secret handshake, AFAR, packages dust production into a single scale with the units of length, albedo A, filling factor F, and aperture radius ρ. Rising AFAR means more dust or brighter dust or both. Steady AVA can hide a nucleus growing more reflective as it spins into a fresher face season. 3I Atlas behaves like a comet, and unlike the ones we've tallied all our lives, which is exactly what we hoped for. Its light curve steepens more than a bare nucleus would as it warms, proof that gas and dust are joining the party. The coma, imaged deep with large telescopes, shows an asymmetric brightness profile that could be a jet or a sunward fan, an active area carrying more of the load than its share of surface. A few nights later, the fan has turned a little, or faded, or doubled, the way a beating heart looks different in the next frame of an ultrasound. Amateur images, processed with care, begin to show a narrow straight feature on the anti-solar side, the ion tail, a thread made not of dust but of charged molecules swept out along the magnetic field, hidden inside the solar wind. Dust is lazier and heavier, its tail curves, obeying sunlight's pressure and the geometry of the viewing angle. The two tails together are sentences in different alphabets. Read side by side, they tell you about gas species, grain sizes, and the wind they are riding. The orbit solution refines with every night of astrometry. Each position reduces uncertainty in the hyperbola's incoming asymptote and outgoing aim. Where did it come from? This is the most tempting question, and the least sensible to answer, with more than a shrug. Backward integrating a hyperbolic path through the galaxy's sea of small perturbations is like throwing a feather in a wind tunnel and asking who exhaled. You can trace the direction, not the home. A trajectory that passes through a local standard of rest does not imply origin in any specific nursery. It is enough to know it is not ours, and to catalogue the composition that says whose it might be like. Days before October, people who work the spacecraft in the Martian orbit begin to whisper about view angles. The spacing works. A pass at a few tenths of an astronomical unit is not close by any standard, except the one that has always constrained our ambitions. Most interstellar visitors do their work where we cannot easily follow. From Mars' orbit, you can look across the inner system at a modest phase angle and see the coma without fighting the sun. The high-resolution camera that sketches rocks the size of chairs on Mars will only ever gather a few pixels from this visitor's heart, far below any level that would reveal shape. But a few pixels are not nothing when you combine them with spectra and light curves and parallax against the same object seen from Earth. Stereo on a solar system scale gives size and activity estimates permission to shrink their error bars. By late October, 3I Atlas will pass its closest point to the Sun. The story around perihelion is an old one told anew. Sunlight deepens in the skin, the thermal wave lags, and ices that only stir at higher temperatures begin to contribute. If water has been slow to wake, it joins. If CO and CO2 have been the early lifters, their ratio to water evolves. Some comets brighten most before perihelion, some after. Some turn brittle and shed fragments you can see as stutters in the light curve and kinks in the tail. For something made elsewhere, even the way the dust reddens with wavelength and the grain sizes implied by tail curvature will feel like dialect rather than accent. If the coma chemistry hints at unusual abundance ratios, enhanced CO relative to water for instance, it will start a dozen papers and 100 gentle arguments in conference hallways about the kinds of disks and temperatures and ultraviolet fields that sculpt planetesimals under a different sun. Upstream of all this, the solar wind is not a uniform river. It is a patchwork of fast and slow streams and shocks, and the magnetic clouds that CMES carry with them. As the visitor threads the ecliptic during an active season, stream interaction regions and coronal mass ejections drift past like weather fronts. The ion tail is a literal field line tracer. When the interplanetary field rotates, the tail kinks. When a shock goes by, the tail can detach and regrow, A sign written in first-year plasma physics chalk, reconnection here. Watching that happen to a body whose ices and dust were cooked under a different star gives us the fanciest natural plasma experiment we could ask for at astronomical distances. The question is not whether solar wind physics changes for an interstellar object, it doesn't, but whether the way material leaves the nucleus and ionizes and couples to fields reveals anything new about grain coatings, volatiles, or microphysics that our familiar comets never quite pin down. Under the coma's glow hides the nucleus, stubbornly unresolved. The trick to guessing its size is to let the dust and gas talk around it. Measure a gas production rate, adopt a sublimation model, how much ice turns to gas per square metre at a given sun distance. Combine them to get an active area, decide carefully how much of the surface you believe is awake, assign a fraction. From that, infer an equivalent sphere's radius. It is a chain with many soft links, each tested by the next night's data. If the rotation period can be teased from light curve wiggles, tiny quasi-periodic changes as jets sweep around with the nucleus spin, then you can ask about torque. Is the spin changing? Is the non-gravitational acceleration measurable in the orbit solution? A polite shove from outgassing that knows the track a few milliarc seconds away from a purely ballistic path? Those tiny accelerations are gold. They say how many molecules are leaving and from where without opening the hood. Comparisons creep in, because we are human, and because the first two visitors left strong impressions. One was slab-like and silent, better at reflecting sunlight than at raising a detectable coma. A puzzle piece that still magnetizes any conversation it's dropped into. The other was a classic, a vigorous coma, a broad dust tail, carbon chains clear as day. The sort of object that could have been labelled a long-period comet if its orbit were only a bit tighter. 3i Atlas sits between those stories and outside them. It gives us gas so we can speak in the chemical language we know. It moves in a plane that makes interactions with solar weather more likely, so we can speak in the plasma language we've spent a career learning. It will be bright enough for modest instruments, so the conversation will not be limited to a few perfect mirrors on mountaintops. It will be shared, flawed, corrected, refined by people under backyards and domes and the thin, dry air of deserts. Night by night the catalogue grows, positions with uncertainties measured in tenths of an arcsecond, photoelectric magnitudes in standard bands cross-calibrated, with notes about thin cirrus and bad seeing and the way a star drifted through the aperture at the worst possible time. Low-resolution spectra uploaded by observers with small grating still catch the shape of the violet CN band. High-resolution spectra from the big scopes, where line widths and profiles carry velocities you can put on a plot with axis labels that make your heart open a little. Radio telescopes try for OH at 18 centimetres, the broken water signature of water production. Infrared instruments chase CO bands that announce cold chemistry waking farther from the sun than water would. If you pull back from the details and let the week blur, the gift of this object is oddly simple. It is strange enough to feel like news and familiar enough to be legible. We do not have to invent a new dictionary to describe what we see, we only have to pay attention to which words are emphasised. Activity turns on at a distance where many long-period comets would still be quiet. That nudges us towards CO and CO2. Dust colour leans redder than a typical Jupiter family comet. That hints at grain coatings, sizes, or processing history under another star's ultraviolet and cosmic ray garden. Ion tail kinks line up more readily with magnetic sector boundaries than with solar wind speed shifts. That says field orientation is telling the story loudest, not dynamic pressure. Each small says is a piece in a mosaic whose picture is not alien so much as kin from a cousin city. 3i Atlas will leave, as all such visitors do. The hyperbola will carry it away toward a patch of sky that most of us could not pick out without help. Long after its coma collapses and the dust tail becomes an unfindable thread among the planet's own debris, the notes we take now will keep it near. Those notes will say that an object forged where we were not, under a sun that was not ours, passed through the plane of our familiar worlds during a time when our own star was restless, and that when its ices met our light and wind, they answered clearly enough that anyone with a small telescope, a notebook, and a steady habit could read along. Imagine a weather map without clouds, only invisible lines and currents you have to infer from the way a single windsock bends. That's how we test the idea that a solar storm brushed 3i Atlas. We don't have a magnetometer riding alongside it, so we watch the windsock, its coma and tails, and we line that behaviour up with the timing and path of an eruption that left the sun days earlier. The chain of reasoning is careful rather than dramatic. First, an eruption is seen in coronagraphs, a bright front, a cavity, a core expanding outward. Its speed in the plane of the sky is measured, its true motion is deprojected using a simple geometric shell model. A drag-based forecast carries it through the inner heliosphere. Then we ask where 3i Atlas was in heliocentric coordinates during that window, and whether a reasonable parcel of plasma with that speed and width could have crossed its path. Only when the times line up do we start reading the windsock. What the solar wind does to a comet-like body begins before any storm arrives. Even in quiet conditions, gas molecules boiled off the surface are ionized by sunlight and by charge exchange. Those newborn ions feel the Lorentz force from the interplanetary magnetic field and are swept away, forming the narrow, straight ion tail that points approximately anti-sunward along the field lines. Dust, heavier and neutral, follows gentler trajectories shaped by radiation pressure, curving into a separate, broader tail. Around the nucleus and inner dust coma, flowing solar wind meets an expanding, conducting gas cloud and drapes its field lines around it, creating an induced magnetosphere with a thin, current-carrying boundary, an ionopause where pressures balance. None of this requires an eruption. It is the steady-state physics of a small outgassing body moving through a magnetized flow. Now bring in a coronal mass ejection. The front of a CME is not a clean plane that has structure, a sheath of compressed, heated solar wind ahead of a more coherent magnetic cloud, often a twisted flux rope behind. The sheath raises dynamic pressure abruptly. The cloud can carry a strong, smoothly rotating magnetic field. As that compound structure sweeps over a cometary atmosphere, several things can happen on timescales of minutes to hours. Increased dynamic pressure compresses the ionopause inward, shrinking the induced magnetosphere and sharpening the inner coma's boundaries. A sudden change in magnetic field orientation can force the draped field to reconnect with differently oriented field lines in the tail. If the rotation is strong enough, the entire tail current sheet can disconnect, literally pinch off, and the downstream segment will drift away as a detached, fading ribbon, while a new tail begins to grow from the head. Those are the textbook signatures, but textbooks don't observe. People do. For 3i Atlas, the signatures we can actually chase with telescopes fall into a few classes. In broadband images, the ion tail may show a sudden kink where the field direction changed, or a notch where a disconnection started, followed by a gap and then a regrown straight segment. The dust tail, governed by radiation pressure and inertia, will generally ignore this drama, continuing its slow, graceful curve. In narrowband images isolating specific emissions, CN-C2, OI, the coma can brighten modestly if ionization rates jump or if sputtering liberates extra material. More often, the shape changes are clearer than the flux changes. High cadence sequences can catch the detached segment literally moving away from the head at a few tens of kilometers per second in projection, a drift measurable over hours. Photometry needs discipline to make any of this persuasive. A constant aperture magnitude will blur inner coma compression and expansion together. An aperture growth curve, a set of magnitudes measured in concentric apertures, can separate the core got sharper from the whole coma got brighter. Observers note seeing air mass, filter and comparison star choices in boring detail, because tail kinks and spurious gradients can be forged by thin cirrus or by a bright field star sliding behind the coma. A good rule is suspicion first, then confirmation. One observatory's kink is an artifact until another, on a different continent under different air, sees it too. Timing is the decisive test. A CME that left the Sun at say 800 km per second and experienced average drag will reach 1 astronomical unit in roughly 2 to 3 days. At 1.3 astronomical units it needs longer, at 0.8 astronomical units less. The feature that actually matters for tail disconnections is not just the arrival of the density front, but the passage of a sector boundary or a strong field rotation in the sheath or cloud. Mapping that rotation to the comet's position uses a Parker spiral estimate of field line geometry and the solar wind speed. It feels like detective work because it is. You take eruption launch parameters, propagate them forward with uncertainties, locate 3I atlas in heliocentric longitude and radius, and ask whether a rotating field would thread the ion tail at the moment your images show a kink. If the answer is yes, within the large error bars, you keep the hypothesis. If the answer is not close, you demote the storm and go hunting for other culprits. An intrinsic outburst, a change in viewing angle, processing artifacts, or background confusion. There is a second flavour of interaction that looks less dramatic but is just as instructive. Tail flutter. Even without a big eruption, compressive waves and stream interaction regions in the solar wind can corrugate the ion tail into gentle bends that move down tail with time. For 3I Atlas, threading the ecliptic during an active part of the solar cycle, this background flutter can be persistent. Distinguishing flutter from disconnection boils down to continuity. Flutter bends and then straightens. Disconnection breaks and regrows. Closer to the head, the ionopause's motion is a subtle proxy for pressure changes. In images with enough resolution, an inner boundary in the blue or violet dominated by ion signals may move inward by a few thousand kilometers when the sheath arrives, then relax as the structure passes. Spectra can showline width changes if the coma's microphysics shifts, more collisions, different ion temperatures. These are second-order effects for modest storms. For strong ones, they add weight to the case. It helps to remember the sequence of the storm itself. The first messenger is light from any associated flare, a spike in soft X-rays and extreme ultraviolet that 8 minutes after leaving the Sun thickens Earth's D layer and would, if 3I Atlas carried a radio, have whispered in its ionosphere too. Hours later, high-energy protons can race ahead along field lines, peppering polar caps on planets and sprinkling spacecraft with extra particle fluxes. Only after a day or more does the bulk plasma arrive, the sheath first, then the magnetic cloud, carrying the field changes that snap tails. The visitor does not care about our indices, but our clocks matter. If the kink appears before the sheath could plausibly arrive, you are looking at something else. Observers can turn this into a community experiment. Agree on filters, broadband luminance for morphology, plus one emission band if possible. Agree on cadences, every 30 to 60 minutes over the expected arrival window if skies allow. Share quick look reductions with timestamps in UTC and plate scales in arc seconds per pixel. Overplot the anti-solar and projected magnetic field directions if you can estimate them. Someone with a knack for coding can fit the bright ridge of the ion tail and quantify its angle as a function of time. A plot of tail position angle versus UT is worth paragraphs. Another person can extract surface brightness profiles along the tail and track the motion of any detached piece in pixels per hour, convert to kilometers per second with the comet-Earth distance, and compare to expectations for alphenic or convective transport. The point is not to be perfect, it is to be consistent. There are false positives. Cometary outbursts, brief increases in gas and dust production from the nucleus, can send a brightness wave down the tail that looks like a moving knot. But an outburst usually brightens the inner coma first and increases the dust contribution. The ion tail responds too, yet the dust tail will also thicken. Disconnections, by contrast, prefer the ion tail and leave the dust largely unchanged. A rotating jet can sculpt a corkscrew in the inner coma that masquerades as magnetic mischief. but it rotates with the nucleus's period. A CME-driven kink advances down tail rather than spinning in place. Changing phase angle can sharpen or blur the whole structure without any space weather at all. That evolution is slow and predictable from geometry. Suppose the case holds, an eruption left the sun, the forecast trajectory grazed the visitor's path within the right window. Multiple observers saw the ion tail pinch and part. A detached ribbon drifted away while a new tail grew. Then the interpretation becomes richer than a single verb like hit. In the sheath, elevated dynamic pressure not only presses the ionopores inward, it also raises the density of pickup ions, newborn ions accelerated by the motional electric field, E equals minus V cross B. Those pickup ions can in turn modify the local field draping, stiffening the tail against the small perturbations, or seeding waves that ripple down the plasma sheet. In the cloud, a coherent field rotation can rotate the entire draping pattern, turning the tail as if someone twisted a dial. A sector boundary crossing where the interplanetary magnetic field flips polarity can feel like a switch. Reconnection proceeds rapidly when anti-parallel fields meet, and tails respond decisively. 3i Atlas offers an extra twist. Its composition and grain properties belong to a different stellar nursery. If its coma's ionization balance favours, say, CO and CO2 over water at a given distance, the mass loading of the solar wind can differ from typical long-period comets at the same R. Heavier molecules and different photoionization rates change the density and temperature profiles in the coma, which in turn shift the standoff distance of the ionopores for the same upstream pressure. A strong storm might therefore drive the boundary proportionally deeper or less deep than you'd expect from an analogue we've seen before. The tail's brightness in specific bands could respond with different lags if photochemistry is slower or faster. Even the polarization of scattered light from dust can tilt if the size distribution and coatings, processed for eons under a different cosmic ray bath, present different surfaces to the sun's radiation. One can go further, though the hour grows late. Measure a non-gravitational acceleration in the refined orbit fit and compare it before and after the storm window. A change would not mean the storm pushed the comet. It would hint that outgassing changed, perhaps because a jet was awakened or suppressed by surface reorganization driven by thermal stress in the days around the interaction. That's speculative, but it is testable with careful astrometry over weeks, folded through a standard outgassing force model. The pieces fit only if the fit is humble, small effects with error bars laid next to other small effects until a trend is visible. If at some point Mars orbiters do secure images or spectra near closest approach, they could add a different angle to the same question. The same kinked tail seen from two vantage points, not just Earth, but Mars, allows a crude three-dimensional reconstruction. The parallax between two lines of sight at interplanetary separations can turn a two-dimensional kink into a three-dimensional fold with a real orientation in space, which can be compared with the magnetic field direction inferred from propagation models of the storm. Even a handful of such stereo points can deambiguate. We think the field turned this way, into the field was likely angled by so many degrees, relative to the solar radial direction. None of this assigns agency to coincidence. Solar storms will pass, tails will kink, sometimes they will do so in the same 24-hour window that also saw earthquakes far away and nova light arrive from long ago. The value in the exercise is that it teaches restraint and method. Establish the solar eruption, propagate it with transparent uncertainties, prepare the observing plan, measure, compare, and label the conclusion clearly. Model consistent brush with sheath and probable field rotation in cloud is not poetry, but it is the sort of sentence that leaves room for the next night's data to agree or to correct. And if, during your watch, you do catch the disconnection, if a bright narrow ribbon steps away from the head of 3i Atlas and drifts into night like a strand of silk, you'll have seen magnetic reconnection not as a diagram, but as a moving, visible cut in a sky that usually hides its fields from our eyes. That is the quiet prize of tying a storm to a visitor, a glimpse of an invisible hand, made briefly plain by something old and cold that wandered in from a different neighbourhood and agreed, for a few hours, to serve as our windsock. Picture a rendezvous that isn't really a rendezvous. Two travellers crossing the same avenue at different curbs, close enough to nod, far enough that neither has to alter their stride. On October the 3rd, the geometry between Mars and 3i Atlas becomes exactly that. A near pass on a cosmic boulevard, roughly a few times 10 million kilometres apart, close in the language of astronomers, spacious in the language of everyone else. What makes this moment special isn't proximity alone, it's vantage. For once, we won't be staring only from Earth's porch. We'll also be peeking from Mars's balcony, and the two views together turn a sketch into a shape. Start with the constraints, because constraints shape everything. Spacecraft in Martian orbit are built to look down, not to chase specks across interplanetary space. Their cameras are optimized for a world, surfaces that fill the field, exposure times short enough to freeze orbital motion, pointing schedules sequenced around ground tracks, power budgets and thermal cycles. To point away from Mars is to break the routine on purpose, roll the bus, retune the attitude control loops, and accept that other observations are paused. There are bright limits. Never point too close to the sun, dark limits, don't starve the batteries, mechanical limits, reaction wheels and gimbals can only do so much. The planners weigh all of it. What they get in return is the chance to look back through the inner solar system at an interstellar visitor gliding behind the red planet's wake. From Mars Reconnaissance Orbiter's high-rise, resolution is a cruel arithmetic. The camera that paints dunes and boulders at approximately 30 centimeters per pixel on Mars's surface from low orbit returns, when asked to stare across tens of millions of kilometers, only a handful of pixels for the entire coma of 3i Atlas. But a handful of pixels is still testimony. With careful tracking, slewing the spacecraft to follow the object's apparent motion, rather than letting it smear, and with long integration stacked and registered, you can resolve a point spread function that is not exactly stellar, slightly broader, slightly asymmetric if a jet or a sunward fan is strong. Even the absence of structure becomes a number, a limit on the coma's full width at half maximum, a cap on how condensed the inner coma is, a clue to how active the nucleus is per unit area. Where imaging is parsimonious, spectroscopy is generous. Instruments like TGO's Nomad or ACS, designed to sniff the thin perfume of Mars's atmosphere, can pivot to sample sunlight filtered through the coma of 3i Atlas instead, searching for familiar molecular bands. CN in the violet is hard from Mars's deck, but in the near-infrared, CO2 and CO leave bold strokes, and water's daughters, OH at 2.8 microns in emission, or H2O features in absorption against reflected sunlight, can shine if geometry and sensitivity line up. The trick is slit placement and background. Place the slit to include the coma and a slice of sky, nod to subtract the zodiacal glow, integrate enough to beat down photon noise, and pray the spectral orders stay clean of Martian airglow and scattered sunlight. The reward is a production rate measured from another planet's vantage, a cross-check on Earth-based numbers that immediately tightens the error bars on volatile ratios. Then there's MAVEN, the weather station in space. It can't see 3i Atlas, but it can feel the wind that 3i Atlas is flying through. Solar wind speed, density, temperature, magnetic field, and the flux of energetic particles near Mars. If a coronal mass ejection or a stream interaction region rolls through that week, MAVEN's upstream data becomes context you can't buy. It tells you whether the tail kinks and ionophores shivers we might see in images make sense given the plasma the visitor faced. In a week of active sun, that context turns "we saw a change" into "we saw a change and we know what pushed." Pointing a spacecraft at a moving target is choreography. You start with an ephemeris, spice kernels for the spacecraft position, a comet trajectory sharpened nightly by new astrometry from Earth. You propagate light time delays so you don't point where 3i Atlas was, but where it will be when the photons arrive. You simulate rates on the detector in pixels per second and ask whether your motion compensation is good enough to keep the coma compact. You run stray light checks. Is the sun far enough from the line of sight that ghost reflections won't wash the frame? Thermal checks. Will holding this pose for 20 minutes creep any radiators out of spec? Momentum checks. Can reaction wheels absorb and bleed the slews without saturating, or will you need a momentum dump that breaks the sequence? Now imagine the images arriving. Stars are streaks if you track the comet. The comet is a streak if you track the stars. Pipelines built for surfaces complain, but the science teams are ready to coddle them. They pull bias and dark frames, flat field the pixels, and then do the most old-fashioned thing in astronomy, measure counts in circles. 1 aperture at 3 pixels for the core, 5 pixels, 10 pixels, 20 pixels for the fuller coma. Subtract a sky annulus. Convert to surface brightness with the instrument's radiometric calibration. Do this for half an hour, 2 hours, and watch. If the inner aperture brightens while the outer stays flat, the ionopore's probably moved inward, a pressure pulse. If the outer brightens first, an outburst may have shed more dust. If the tail position angle, measured as the ridgeline of the faintest isophotots, swings by a few degrees over an hour, something in the field changed. None of this is dramatic, all of it is legible. Parallax is the quiet star of this show. From Earth, you measure the comet's position in the sky with an accuracy of a fraction of an arc-second. From Mars, you measure it again. The separation between the two observers is tens of millions of kilometers, and that baseline turns angular differences into distance. Distance feeds back into absolute magnitude and production rate estimates, freeing them from assumptions that couple brightness too tightly to composition models. If Earth and Mars observers can synchronize even a few simultaneous measurements, careful UT stamps, coordinated exposures, the two-point geometry clips off a limb of uncertainty that would otherwise remain flailing months longer. Phase angle, the Sun-Comet observer angle, matters too. From Mars, the phase might be lower or higher than from Earth by tens of degrees. Lower phase compresses the dust tail's brightness into a narrower glint. Higher phase enhances forward scattering by small grains, brightening the coma and tail disproportionately. Comparing brightness and profile shape at 2 phase angles on the same day is the kind of gift you usually wait weeks for as orbits plod along. On October the 3rd, it shows up all at once. There are limits worth stating plainly. No spacecraft will resolve the nucleus as anything but a point. The coma will be barely more. Any shape we infer is statistical, dragged out of PSFS and azimuthal profiles. But small constraints are cumulative. If the inner coma's brightness falls off with radius as Warrow to the negative first power, the steady, spherically symmetric outflow law at one epoch and steepens temporarily during the pass, that's a fingerprint of interaction or geometry. If a jet's position angle matches a periodic modulation in Earth-based light curves, that ties rotation period to feature for the first time from a second vantage. If non-gravitational acceleration measured from weeks of ground-based astrometry shifts slope after perihelion, and Marside spectra show a changed CO2/H2O ratio, a coherent picture emerges. One set of vents shut down, another woke. Observation teams will lean on redundancy. Mars Express's Amiga or HRSC might grab context while TGO chases lines. HiRISE will collect a few deep frames while MARC or CTX, with their wider fields, record where the tail lays against the star field for easy registration later. On Earth, an army of small telescopes will keep the cadence that big spacecraft cannot, every 10 minutes where weather allows, measuring the coma's photometry and the ion tail's angle, while the spacecraft delivers sparse but exquisite slices. ALMA, if scheduling and constraints cooperate, can go fishing for rotational lines of CO that anchor gas production in absolute terms rather than in proxies. A handful of radio dishes will listen for OH at 18 centimeters, the water breakup tracer that still makes comet observers feel like radio magicians when it whispers back. Even planning has physics in it. Exposure time is a bet. Go too long, and tracking errors and drifts start to bloat the core. Go too short, and read noise dominates and faint structure vanishes. Teams will bracket just as photographers have always done. They'll take a set at short exposures to freeze the core, a set at medium to smooth noise, a few at reckless, long times to see how far the tail really runs before it drowns in zodiacal light and instrument scatter. They'll rotate fields where possible to separate optical ghosts from honest structure, dither to average down pixel-level quirks, and tuck calibration frames before and after in case the detector's temperament shifts with temperature over an orbit. Because the pass happens during a busy solar season, interpretation will refuse to be simple. A tail kink seen from Earth at 310 UTC might be a disconnection. From Mars at 325 UTC, the same structure could look less dramatic because the viewing geometry projects the fold differently. Maven might record a southward IMF turning at 2:40 AM at Mars, while L1 spacecraft report a northward field at Earth at 3 AM. The Parker spiral and radial separation explain the mismatch. What matters is not that every dataset tells the same story in the same accent, but that each makes sense given where it stood and what it could sense. There is a romance to the numbers that doesn't make it into press releases. Someone will sit at 3 o'clock local time with a mug gone cold, typing ephemerides into a planning tool that was never meant for this, finessing a pointing offset by 1/10 of a degree because the latest orbit solution nudged the track. Someone else will graph tail position angle versus UT from 5 observatories spread from Namibia to New South Wales and see a gentle, coherent swing that says the interplanetary field turned as a sector boundary slid past. A spectroscopist will subtract 2 Mars-side spectra and find a shallow real change in the CO2 band depth over 3 hours, and they will send a note that simply says, "It moved." If 3i Atlas throws a surprise, a fragment shedding, a sudden outburst, it will upend carefully rationed integration times and fill plates with urgency. If it does nothing but behave like a well-mannered, CO-rich visitor, it will still be the first time we have watched such a thing from 2 planets at once, while the Sun actively remodels the medium in between. That alone turns a crossing into an experiment. Measure the same coma in 2 lights, in 2 phase angles, through 2 windows of atmosphere, thin, Mars, thick Earth, under 1 wind that we can now characterize in situ. When the sequence ends, the spacecraft will roll home to their normal lives. Weather maps, mineral maps, limb scans, occultations, and the data will go to vaults where it is harder to misplace than it used to be. Teams on Earth will fold the Mars numbers into their own fits and publish figures where red and blue points, Mars and Earth, march together along the same curve with a respectful parallax between them. The intangible gain will be a calibration of ambition. The next time an interstellar passerby cuts near the lanes we travel, we will not argue about whether we can point an aero braking mapper at it for 20 minutes. We will point because once we did, and the handful of pixels and narrow lines and parallax and plasma logs were worth every constraint bent for an hour in the calm mathematics of an October pass. There's a moment in any crowded week when your brain quietly reshuffles the cards and decides that the hand you're looking at must have been dealt on purpose. 2 novae bright enough to chase with binoculars, 2 mid-6 earthquakes separated by a few hours on the same patch of crust, a run of coronal mass ejections threading the inner heliosphere, an interstellar visitor, 3i Atlas pacing through the ecliptic like a courier who has seen too many cities to be impressed by ours. If you list these in a column and draw lines between the dates, a shape emerges that feels less like weather and more like design. That feeling is real. The design almost always is not. What your mind is doing has a name in statistics and in psychology. The law of small numbers says we instinctively expect small samples to behave like large ones, sprinkling drama evenly when in fact randomness clumps. The Texas sharpshooter fallacy invites us to fire 1,000 shots at a barn and then draw a bullseye around the tightest cluster and declare aim. The availability heuristic elevates what you just saw into what must be common, and the recency illusion makes last week feel like the template instead of the exception. But a fast news cycle on top of that, where editors rightfully promote unusual events, and coincidence stops feeling like arithmetic and starts to feel like plot. The antidote isn't to harden your heart against wonder, it's to develop a habit of model-first thinking. Before you ask, do these events go together? Ask, what would together even look like if nothing were connected? Give yourself a null model. For earthquakes, a good null isn't a perfectly random Poisson drizzle. Real catalogues are clustered because aftershocks are part of the physics. So you use ETAS, an epidemic-type aftershock sequence model, as the backdrop. Main shocks spawn children that spawn grandchildren, all decaying in time and space with a Mori-Utsu's law. For novae, the null is a calendar drawn from historical rates and magnitude distributions, a dozen or so galactic novae per year, with one or two getting bright enough for small optics every few years. For solar storms, the null is the cycle. Maxima load the dice toward weeks with multiple CMEs and strong indices. For interstellar visitors, the null is brutally sparse. We've seen 2 before. A third within a decade is unlikely, but not absurd given how much better our surveys have become. Now you can test a feeling without scolding it. You line up absolute dates, not vibes. You define a time window ahead of time, say September 20th to 30th, and ask, how often would ETAS plus nova rates plus solar maximum T ME frequencies plus the unconditional presence of 3I Atlas, already discovered, produce a week with 2 naked eye novae, 2 greater than or equal to 6 quakes in the same region, and at least 1 Halo-class CME? You run 1,000 resampled worlds. If it's 1 in 50, that's uncommon, but hardly cosmic. If it's 1 in a million, you've either found something interesting or overfit your question to the week you lived. When people talk about synchronicity, they often mean the subjective experience that a few large clocks, star death, tectonic slip, solar breathing and interstellar drift briefly tick together in a way that felt legible. It is useful to separate legibility from linkage. Legibility is a property of humans, our sensors, our networks, our attention. Linkage is a property of nature, a mechanism that moves energy or information from one domain to another, on a time scale and at a magnitude that matter. Most of the time, legibility increases while linkage does not. We watch more, we notice more, we thread more lines between more points. The underlying couplings, the slow trade between plates, the plasma rules in a hot magnetized wind stay the same. This isn't an exhortation to stop drawing lines. It's an invitation to do it cleanly. Pre-register your question. Decide which catalogues you will use, which thresholds count as events, how wide your time windows are, and how you'll correct for multiple comparisons. If you're testing 20 different linkages, sunspot number to global seismic rate, DSD index to mid-latitude earthquake timing, number of CMEs to nova brightness, you don't get to celebrate the one that pops at P equals 0.04 and forget the 19 that didn't. That's not how truth is found, that's how folklore is made. There's another way to protect your curiosity. Keep base rates in view. A magnitude 6 earthquake happens somewhere on Earth about once every few days. CMEs launch from an active sun many times per week. 2 novae in a week isn't common, but it's not an eclipse of the century either. 3I Atlas isn't the first interstellar object, and it's arrived in an era when our sky sweeps are deep and fast. Given those base rates, clusters will occur by chance with some frequency. When they do, the right response isn't to flatten them into nothing to see, but to ask the next question with humility. If there is linkage, what would the mechanism be? How big would the effect need to be to matter? And, crucially, does it have predictive skill that beats a boring baseline? That last phrase is the line in the sand. Hindsight is cheap. Predictive skill is rent. If, on September 20th, you had written a note that said, given current solar wind and active regions, expect a twofold increase in the probability of greater than or equal to M6 earthquakes in northern South America between the 23rd and 26th, and you had reasons you could defend before anyone saw the outcome, and you were right more often than chance over many such windows, then you would be allowed to talk about linkage. Without that, you have a story, and that's fine, just label it honestly. So what about the oldest story in this niche, that space weather nudges the solid Earth? It's persisted since people first tallied sunspots by hand and earthquakes by hearsay. The modern version comes with better sensors and fancier acronyms, but the same core question, can variations in the solar wind and magnetosphere, X-ray flares, proton events, geomagnetic storms, alter stresses or friction enough on crustal faults to measurably change the timing of earthquakes? Start with scales, because scales are where bad ideas go to retire. Earthquake failure is governed by effective normal stress and shear stress on a fault. The Coulomb failure criterion says that a tiny positive change in shear stress or a tiny negative change in effective normal stress can advance failure on a patch that's already close. Typical dynamic stress drops in earthquakes are tenths of a megapascal to a few megapascals. Static Coulomb stress changes that meaningfully alter rates on neighbouring patches are on the order of kilopascals to tens of kilopascals. Earth tides, gravitational flexing from the moon and sun, apply stresses of order 1 to 10 kilopascals and do, in some settings, weakly modulate seismicity in a phase-locked way. Barometric pressure swings are hundreds of pascals to a few kilopascals. By contrast, geomagnetically induced currents and their associated electromagnetic fields couple into the crust to produce equivalent stresses, typically orders of magnitude smaller, pascals to tens of pascals, unless you're in a very conductive, fluid-rich setting where pore pressures can be levered a bit more. A change of 10 pascals is 0.00001 megapascal. That is 4 to 5 orders of magnitude below typical earthquake stress drops, and 1 to 3 below the smallest static stress changes we routinely see affecting aftershock rates. You can't declare this irrelevant on site. Faults near criticality are touchy, but you must concede the physics is starting far underwater. Proponents of coupling point to a few pathways. One is electromagnetic induction. Geomagnetic storms drive ionospheric currents. Time-varying fields induce electric currents in the crust. Those currents could, in principle, alter effective stress via electroosmosis or electrochemical effects along fluid pathways. Another is direct mechanical. Solar wind dynamic pressure changes the magnetosphere, which modulates atmospheric pressure and ionospheric currents, which might alter surface loading by trace amounts. A third lives in the ionosphere itself. Claims of pre-earthquake total electron content to T. Anomalies suggest that stressed crust emits upward propagating ULF waves or charged aerosols that alter ionization overhead, sometimes days before large events. And there are piezoelectric whispers. Quartz-rich rocks under stress could generate fields that couple upward or outward. Every one of these has a first principles problem or a statistics problem or both. Induction works, but the measured field changes in the crust are tiny compared to tectonic stresses. Electroosmotic effects require well-connected, appropriately scaled fluid pathways right where you need them, and those don't line up generously on command. Surface loading from magnetospheric pressure is several orders below the ordinary swings from weather and tides, which again show at best weak modulation. Tech anomalies are seductive because GNSS receivers give you tech with fine cadence almost everywhere. The trap is confounding. Tech moves for many reasons: solar flux, geomagnetic storms, tides, local time, season, and unless your study is pre-registered, controls for these confounders, and makes out-of-sample predictions, you will find ghosts. The ULF literature is littered with post-event excavations of interesting wiggles near big earthquakes that do not replicate prospectively and vanish when you control rigorously for power line noise, magnetic storms, and instrument drift. If you wanted to give the hypothesis its best chance, you'd run it like this. Physically, you'd build a stress budget at faults. Tidal, barometric, hydrologic, tectonic, and a carefully modelled electromagnetic induction term driven by real magnetometer and ionospheric current data. You'd quantify the electromagnetic term's amplitude at depth for realistic conductivity profiles. Statistically, you'd construct a point process model for earthquakes in your region, ETAS for clustering plus a time-dependent baseline rate lambda 0 of t that you allow to depend on hypothesized drivers, KP, DST, AE, solar wind dynamic pressure, BZ, TEC. You'd pre-register which drivers you include, what lags you will test, and your evaluation metric, likelihood improvement, Breyer score, area under the ROC curve, against a naive baseline that uses no space weather terms. You'd train on one decade and test on the next. If your model's predictive skill, measured prospectively, beats the baseline by a margin that survives correction for multiple testing, you'd have something worth arguing about. If not, you'd publish the null result, because that's how a field learns. The most honest successes in this area tend to be specific and small. Seismicity in certain tidal bands increases slightly for very shallow normal faults in coastal settings, phase locked to the fortnightly tide. Swarms near volcanoes correlate with pressure, diffusion, and gas flux changes rather than with geomagnetic indices. Pieces of crust near big reservoirs show increased microseismicity as water levels change. A reminder that kilopascal scale perturbations can matter when faults are primed and fluids are mobile. None of these require the sun. They require patience and the humility to separate can from does. The same humility would serve any claim that a G3 storm tomorrow will trigger a magnitude 7. It is not impossible in the logical sense. It is unsupported in the physical and statistical sense. There is a softer argument for why the story persists even when the math is unforgiving. It is narratively satisfying for sky and ground to talk. Human time is thin, cosmic and tectonic time are thick. A week that compresses their clocks into something you can hold feels like a note from a larger book. And sometimes, with the right experiment, the sky and ground do talk. Solar storms rewire our ionosphere and paint geometric ovals with light. Earth tides tug on faults, and by a percent or two alter the odds of a slip. Lightning steps from cloud to ground through fields that precondition air the way stressed rocks precondition themselves. These are couplings we can derive, measure, and predict. They make room for wonder without making room for wishful thinking. If you are tempted to join the hunt, and it is a good hunt, because even negative results sculpt truth, keep a few heuristics handy. Magnitude first, estimate orders. If your mechanism cannot plausibly generate greater than 1 kilopascal of stress change at depth, it is unlikely to affect anything but the most precariously balanced patches, and your signals will be statistical whispers. Phase matters. Tidal and diurnal couplings should produce phase-locked responses. If your effect drifts freely, be skeptical. Controls are not optional. You must remove aftershock sequences before you go fishing for subtle drivers, or your model will mistake Amori's law for solar magic. And prediction beats post hoc. Make a forecast, timestamp it, and keep score. In the week that set this essay in motion, the safe, testable couplings are enough to keep us busy. The sun's field rotates. An ion tail kinks and detaches on 3i Atlas and regrows like a lizard's. A pair of ruptures light up a stress map across a Venezuelan fault system, and aftershocks trace the lobes where static stress rose. The auroral oval swells equatorward under southward BZ, and starstruck people stand under green arches where they have never stood before. A nova's soft X-ray phase clicks on as its ejecta thin, and spectrographs catch hydrogen recombination lines narrowing as velocities fall. Each of these is a mechanism embedded in numbers, available to anyone with a modest instrument and a habit of care. If a deeper linkage exists between them, it will declare itself the same way, by turning "I notice something" into "I can show you a signal" that survives its own skepticism. Climate is a slow accountant. It balances energy in and energy out over spans that dwarf headlines. To ask whether a nova can tip those books, you start with units that don't care about ore. A nova radiates roughly the sun's power for a few days to weeks, and, integrated over time, totals on the order of 10 to the 38th to 10 to the 39th joules. Astounding by human standards, still minute when diluted across interstellar space. A supernova releases many orders more energy in light and particles, but again distance is everything. Flux falls as 1 over the distance squared. By the time photons from even a bright galactic nova reach us from thousands of light years away, they amount to a sprinkling of extra starlight, not a new heat source. Compare that to the solar constant, approximately 1,361 watts per square metre, every day, every cloudless noon. If all the light from a typical nova was somehow focused on Earth at its peak for a week, it isn't. The added average flux would still be lost in the round-off of weather. It's not radiant heating that intrigues scientists when they speak of stellar explosions and climate, but chemistry and particles. High-energy photons, X-rays and gamma rays, from a sufficiently nearby supernova can dissociate nitrogen and oxygen in the upper atmosphere, catalyzing ozone loss and letting more solar ultraviolet reach the ground for years. That is the mechanism with teeth, but the range for serious bite is short, tens of light years, not thousands. For novae, which are intrinsically dimmer in hard photons and typically far, the photon bath at Earth is gentle, its chemical leverage is negligible. Their light arrives like a poem, not a policy. Cosmic rays, accelerated in supernova shocks, travel farther and take longer. And here the conversation stretches across geologic time. They do not heat, they ionize. Ion pairs formed in the middle and upper atmosphere concede microphysical pathways that may, under certain conditions, modulate aerosols, cloud condensation nuclei, and cloud properties. But may does a lot of work. The microphysics is contingent on altitude, on sulfuric acid availability, on ammonia, on temperature, on existing aerosol burdens. Laboratory experiments have shown that ionization can aid nucleation in very clean air. The leap from a nanometer scale cluster in a chamber to global cloud cover is many leaps. Observationally robust predictive correlations between cosmic ray flux changes and cloudiness have proved elusive once confounders, ENSO, volcanoes, seasonality, circulation patterns are properly sorted. The null hypothesis that the sun's modest 11-year modulation of galactic cosmic rays imprints only a whisper, if anything, on the climate system, still fits the data as well as anything. There are, however, direct fingerprints of nearby supernovae written in Earth's sediments that do not depend on clouds. The isotope iron-60, forged in massive stars and their explosions, has been found in deep-sea ferromanganese crusts and lunar soil. Its half-life is short on geologic terms. Its presence signals dust from supernovae arriving at Earth a few million years ago. That's cause and effect, not conjecture. What those pulses of extra cosmic radiation and dust did to climate and life is an open, careful question. Some researchers have explored links to subtle biotic turnovers or long-term climate trends. Others emphasise that the signal could have been quite modest at the surface, with more pronounced effects in the upper atmosphere and on radiation doses. The important habit is scale discipline. Even nearby in this context is hundreds of trillions of kilometres. Even enhanced radiation can be small compared to the day-to-day variability of the lower atmosphere driven by oceans, volcanism and greenhouse gases. If we return from supernovae to novae, the 2 September eruptions that shared our sky, what remains is wonder without worry. Their photons traversed millennia to us, softened by dust and distance into spectacles that teach astrophysics, not climate. They remind us that high-energy events can accelerate particles to relativistic speeds in tiny volumes via shocks and reconnection. That binaries can be engines of chemical enrichment, that dust can condense and re-radiate like embers after a flash fire. Their contributions to the interstellar medium lithium, aluminum-26, dust grains, matter to galactic ecology, not to this autumn's weather. If you insist on a climate takeaway, it is a meta one. The climate system is dominantly local in its forcing. The sun's brightness, volcanic aerosols, greenhouse gases, land surface changes, these set the baton. Distant novae are music we enjoy while the orchestra plays on. It is tempting to smudge the categories, to let the phrase space weather bleed into earth weather, and then into climate, because the words rhyme, and the pictures from space are so vivid. Precision asks us not to. Space weather couples to technology and to the upper atmosphere on hours to days scales. Radio blackouts, auroral currents, satellite drag. Weather couples to people over days to weeks. Storms, heat waves, precipitation. Climate is the average of weather and its low-frequency modes over decades and longer. The couplings between these tiers are real but weak. A severe geomagnetic storm can increase satellite drag enough to alter how quickly launched debris re-enters, which can affect operational risks, which can affect scheduling. That is a chain of influence. A nova can put a fresh line in a spectrograph and a fresh photograph on a wall. That is a different chain entirely. When you switch the question, how can novae influence Earth, to a more fertile one, what can an interstellar visitor tell us about the Sun? The arithmetic flips from dilution to amplification. Small bodies with comae are exquisite detectors of magnetic structure and plasma conditions. They are mass-loading machines. Every neutral that goes iron is a new hitchhiker that the solar wind must accelerate, changing the local Alfvén speed and draping pattern. They carry their own neutral atmospheres and ionospheres into the wind, building thin current sheets and boundaries whose shapes respond to pressure and field like a leaf responds to eddies. Treat 3I Atlas as a probe, and the checklists write themselves. The ion tail traces field direction. The standoff distance of the ionopause encodes the balance between outflow pressure and solar wind dynamic plus magnetic pressures. The frequency of tail disconnection events hints at how often strong field rotations or shocks traverse its orbit. In situ magnetometers would be ideal. Short of that, we measure carefully, often, and from multiple vantage points. A network of imagers can fit the ion tail's position angle and curvature every hour and plot it against solar wind models propagated from L1, STEREO, or Parker Solar Probe with the proper spiral geometry. Mismatches teach us where the forecasts are wrong. A Mars-side spectrum of CO and COD, two production rates, placed beside Earth-side OH line strengths, yields volatile ratios that through simple energy balance models give active area estimates. Those fed into analytical coma models, Hazer or more sophisticated Monte Carlo neutral flows, output density profiles that feed back into where the ionopause should be for a given upstream wind. Pickup ions are the most eloquent actors in this play. A newborn ion sees an electric field minus V cross B and begins a cycloidal dance around the magnetic field at the local gyro frequency. The ensemble of such ions forms a ring beam distribution that can drive waves and turbulence, modifying the shock structure if a CME is passing. If you had a mass spectrometer nearby, you'd watch composition change with radius H2O+, OH+, CO+, CO2+, and infer parent molecules and ionization rates. Without one, you infer from light, the brightness and thickness of the narrow ion tail in specific bands, the velocity widths of emission lines that respond to temperature and turbulence, the spatial offsets between dust and ion features when a pressure front compresses the head, even polarization whispers. Linear polarization of dust-scattered sunlight grows with scattering angle and grain size distribution. A spike in polarization at fixed phase angle can signal fresh small grains from a jet turning on, which in turn points to a vent location and rotation phase. Draping is more than a diagram, it is a map we can make. In the simplest picture, field lines bend around the obstacle, forming a magnetotail aligned with the mean flow and field. But the draped field's pitch angle depends on the ratio of flow speed to Alfvén speed, on mass loading, and on the obstacle's outflow geometry. Measure the tail's opening angle and ridgeline from Earth and Mars at the same time, and you can invert for the local field's orientation and strength within model families. Do this through a week when a corrotating interaction region sweeps past, and you've drawn a time-dependent 2-point map of the heliospheric current sheet's neighbourhood using nothing but photons. Charge exchange provides yet another diagnostic. Fast solar wind protons can steal electrons from the neutral coma, becoming energetic neutral atoms, ENAs, that fly ballistically. Dedicated ENA imagers at the right distances have made global pictures of magnetospheres. With 3i Atlas there will be none nearby, but the consequences of charge exchange remain. A faint soft X-ray glow from solar wind charge exchange, SWCX, in the coma. With sensitive X-ray telescopes, that glow can, in principle, be mapped to separate where solar wind ions interact with dense neutral gas versus where UV photoionization dominates. Even a detection without a map is a constraint on the product of wind flux and neutral density. Mass loading itself slows and heats the wind. The slowing moves the bow shock if one forms and the cum-toe pours outward. The heating can be seen as broadened line profiles in ion emissions and as a thicker, fuzzier ion tail close to the head. When a CME's sheath arrives, dynamic pressure jumps, the come-to pause shrinks, magnetic field strength rises, draping tightens, reconnection proceeds at new boundary orientations. If a magnetic cloud follows with a coherent rotation, the tail swings through a suite of angles that, plotted over hours, are a Rosetta Stone for the cloud's axis direction and handedness. In effect, 3i Atlas becomes a remote magnetometer for a structure we cannot sample in situ, and it not only tells a storm, but this kind of storm. Composition, of course, is the extra dividend that makes interstellar visitors precious. Solar system comets are time capsules from the outer disk that built our planets. An object like 3i Atlas is a capsule from some other disk, built under another newborn star's ultraviolet field, with different dust-to-gas ratios and grain coatings, perhaps a different nitrogen budget, perhaps a different inheritance of pre-solar grains, spectra of CN, C2, C3, H2, OH, CO, CO, 2, and the forbidden OIC 30 nanometer line, folded through realistic fluorescence efficiencies, G factors, give production rates. Their ratios tracked from 2 AU to perihelion and out again. Sketch which volatiles drive activity at which distances, and whether layers of different composition are being uncovered as seasonal illumination changes. If CO stays strong relative to water at smaller R than usual, that points to unusual abundance or unusual permeability. If dust colour and polarization differ from garden variety comets at the same phase, that implies different grain sizes or mantles, perhaps a processing history in a denser cosmic ray environment that hardened organics differently, rotation couples composition to plasma in a way that makes time your ally, a nucleus that spins carries vents in and out of sunlight and the wind. Repeating features in the coma, fans, jets, carry the spin period in their appearance and orientation. If a jet dominates, it can torque the nucleus, measure a change in period over weeks, and you have a direct gauge of outgassing forces. Those forces also leave non-gravitational fingerprints in the orbit solution. Tiny, sunward-oriented accelerations that shift the hyperbola's shape by micro-arc seconds per day. Fit them with the standard outgassing law, and you fold dynamic and photometric data into a single self-consistent picture. None of this requires perfect instruments. It requires cadence, coordination, and humility about uncertainties. A dozen small telescopes logging tail angles every hour do as much for field orientation as a single large frame taken once. 2 spectra from different planets taken within the same hour, with their different phase angles and airglow backgrounds, tell you more about Coma's structure than 5 spectra from one site across a night. A magnetometer at Mars and a model propagated from the Sun to Earth, interpreted together with tail morphology, beat a model alone. The discipline is to annotate everything: aperture sizes, filters, seeing, air mass calibration stars, the position of the antisolar vector in each frame. Then you can ask specific questions of the universe and accept specific answers. What makes an object like 3i Atlas a probe in the truest sense is precisely that it's not ours. It carries a chemistry set from an alien pantry into our wind, and the way our wind treats it reveals both what the wind's doing and what the pantry stocked. Magnetic reconnection that slices ion tails cares not at all about provenance. The rate, the geometry, the growth of the X-line are plasma business as usual, but the luminosity of the slice, the cooling time of the newborn ions, the scatter in tail width, all these whisper about the atoms involved. You can separate how from what by watching carefully as the sun does what it always does and the visitor answers in a slightly different accent. There is a larger, quieter point in turning a passerby into a measurement. The heliosphere is not a static bubble. It is a breathing, rotating, seasonally tilted machine threaded by current sheets and punctuated by ejecta. We have a few thermometers inside it. Parker Solar Probe Solar Orbiter STEREO, sentries at L1 and sometimes L5. Objects like 3i Atlas let us hang a windsock in places those thermometers are not. For a few months, at scales our eye can still pass with photons. It's a temporary installation, erected by coincidence and demolished by orbital mechanics, but while it stands, it reads the flow. If we read it well, we not only learn about one visitor, we calibrate our models of the wind and the storms that ride it, using nothing more exotic than light and careful habits. Circle the dates, but also circle the uncertainties. October 3rd is geometry, not spectacle. A near pass with Mars that trades proximity for parallax, a chance to see the same Coma and tails from 2 planets at once while the sun's wind provides the moving background. Expect a handful of deep frames and narrow spectral slices from orbiters, a flurry of simultaneous Earth-side images, and, if solar weather cooperates, a visible kink or compression in the ion tail that reads like a sentence about the field at that hour. If nothing dramatic happens, that outcome is still rich. Nulls are constraints. The absence of a kink during a forecasted sheathid arrival can impeach the forecast, not the physics. The refusal of the ionopores to budge within error bars can whisper that the visitor's mass loading is stronger than we assumed. A thin kind of victory perhaps, but real. October the 20th to 21st is a different rhythm. A weekend for naked eyes and small optics. New moon sets the stage. The Orinids steal attention with quick needles from Halley's debris, and a second comet threads the scene while 3i Atlas continues its slower dance. If skies are mercifully dark, you should be able to step outside with binoculars and see not just the point of the nucleus, but the lived geometry of comets. Coma bright near the head, a wispy tail turned away from the sun, perhaps a surprise fan if a jet carries its own stubborn direction. The Orionids will arrive in fits and starts, glowing green or white and leaving brief trains. The visual trick for a meteor shower is patience and averted vision. The intellectual trick for 2 comets at once is map and memory. Print a chart, mark positions for each hour, and sketch what you actually see rather than what you meant to see. A quick, honest graphite scribble of a faint fan that isn't in the coffee table photographs may be the only record of a transient feature when clouds roll in for everyone else. October 29th is heat, not closeness. Perihelion is when seasonal physics, Not Earth seasons, but surface seasons on the nucleus decide which vents take the lead. You may watch the total brightness drift, bump, or stall. You may see the coma change texture as grains of different sizes and chemistry dominate. You may catch an outburst as a crusted patch fails and a small avalanche of brightness races down the tail. Photometrists, this is your vigil. Standardized filters, V or R prime, are the workhorses. Standardized apertures report the radii as projected kilometers, not just arc seconds, so others can compare, and log sky conditions with the same care as the numbers. Spectroscopists, your signatures change subtly with temperature and flux. Lock your calibrations and cadence them through the nights before and after, so a curve emerges rather than two unhelpful points. Casual watchers, your contribution is steadiness. Go outside, look up, write down. The night after perihelion often tells a more complete story than the night itself. Between these waypoints, space weather wraps its own calendar around everything. Autumn brings the Russell-McFerrin geometry into play. The magnetosphere is, on average, more permissive of coupling. If the interplanetary field leans south and stays there for a few hours, aurora unfurls, GPS delays wobble, HF radio reports turn into impromptu science logs, and polar flyers cross-check their comms plans against the routes that look good on a whiteboard and less good under a storm. It has become customary to treat auroras as a photo op, but remember it is also a reconfiguration of currents at planetary scales. If you go north to watch, take a hat and a histogram. Dress warmer than you think you need, and expose for the greens and reds so you don't turn a living sky into clipped paint. If you stay home, keep an eye on indices and on the humble magnetometer traces posted by schools and amateurs. They render a storm as a line that dips and climbs, an EKG you can read with no training and honest wonder. November is the month of reckoning and mundane delights. By then, 3i Atlas will be sliding away from the sun on the far side of its hyperbola, cooling enough that water-driven activity may wane, while more volatile ices continue to carry the load. If the Mars observations yielded spectra, we'll have first looks at ratios CO2/H2O, CO/H2O that will seem alarmingly precise and should still come with fat error bars. If the near pass with Mars happened under a CME, papers and preprints will begin to sketch the 3D orientation of the magnetic cloud using nothing more exotic than two sets of tail angles and a Parker spiral assumption. Amateur campaigns will settle into cadence work, one image each clear night, roughly the same local time, roughly the same aperture, roughly the same processing so that a week looks like a sentence rather than 7 syllables. You will hear complaints about weather and processing software, about flats and fringing and the star that always slides into the aperture at the wrong moment. Those complaints are the sound of the work actually happening. December 19th is close, by the scale of planetary orbits, not by the scale of the eye. At approximately 1.8 astronomical units, we're still talking telescopes, not porch steps. The gift is geometry, longer path lengths in the coma for line-of-sight integrals, better SN for spectra, and a phase angle that may swing into a sweet spot for forward scattering by small grains, making the dust tail punch above its weight. Use that. Repeat your November measurements with the same discipline. If you chased polarization, do it again. Polarization curves as a function of your phase angle, are fingerprint-level diagnostics of grain size and structure. If you attempted EF in October and felt foolish, try again and be less foolish. Practiced hands are not born, they are made. If you only ever looked, look again. The point of a long apparition is not to make you stare at the same thing. It is to let you watch it change slowly enough that the change feels like learning, not luck. January and February will be quieter and more interesting than anyone predicts. If the visitor behaves, you'll see brightness decline and structure simplify, and that will be a graceful thing to draw and compute. If it misbehaves, fragmentation, a late outburst, that will complicate numbers and thrill people who enjoy plotting multiple slopes on the same log-log axis. Either way, By then we will be in the realm of synthesis, fold solar wind reconstructions through the weeks of October and November, match tail kinks and ionopore's motions to interplanetary drivers, and let the mismatches teach you humility about models. Take the Marside spectra and Earthside OH lines and squeeze them through Hayser or vectorial models until production rates line up with long-range non-gravitational accelerations. If those accelerations change sign or slope, ask not for miracles but for geometry. Did the subsolar latitude on the nucleus drift far enough to hand the baton to a new vent? If a rotation period estimate from jet modulation shows a secular torque, feed that back into the force model. Let dynamics, photometry, and chemistry argue politely until they agree. Alongside this, keep an ear on the ground. Aftershock sequences in Zulia will have faded but not stopped. The long tail of Amori and the subtle reloading from visco-elastic relaxation at depth will continue to write small events into catalogues that few will read and many will benefit from. Preparedness is not content. It is furniture. Fasten bookcases, store water, know your gas shutoff. Revisit your family plan this winter, using the week in September as your reason and your story. It is easy to put cosmic dates in a calendar and hard to put fresh batteries in a flashlight. Do both. Ambition should be calibrated, not muted. For the remainder of this year, the best versions of what to expect are simple. Modest visual displays, strong science if cadence is respected, occasional space weather mischief that makes good television and better graphs. The worst versions of what to expect involve nouns like harbinger and verbs like unleash. No one owns your attention but you. Use it as capital. Seek out the places where numbers are shown alongside adjectives. Reward humility with your clicks. Ask repeatedly, what would disconfirm this? If the answer is nothing, you are in a story, not a result, and stories are delicious but ought to be labelled. For anyone who wants to do more than watch, who wants to turn a season into a small, well-run experiment, the playbook fits on a single messy desk. Start with a logbook that isn't your memory, paper, notes app, spreadsheet, anything you will actually use. Date and UTC time at the top of every entry, weather, seeing, transparency, gear used, any deviations from your usual workflow. Add a column you're certain you will never need. That's the one that will save you when your future self asks a question you didn't know to ask. If you have binoculars or a small telescope, commit to a cadence. One observation every clear night beats 4 in a week, followed by silence. Sketches are data when they're dated and labelled. So are verbal descriptions if they name comparison stars and list approximate magnitudes. If you have a DSLR or mirrorless camera, find a fixed tripod, shoot 3 to 10 second exposures at high ISO in RAW, and stack them later with simple software. Do not chase social media noise reduction. Grain with detail beats smoothed ghosts every time. If you have a tracker, keep exposures short enough that field rotation and periodic error stay well below the width of the coma. If you want to try photometry, start in a standard band. V or R are friendly. Download a sequence of calibrated comparison stars from a catalogue, APASS, pan-stars transformed. Keep your aperture and annulus consistent and report your 0 point and uncertainties honestly. Transform to the standard system if you can. If you can't, say so. If you want to try AFR, measure surface brightness in concentric apertures and compute AFR at a fixed projected radius so you're not conflating optics with coma physics. It will feel like sorcery the first time, then like math, then like a ritual you can do tired. That progression is the point. For a spectra, even a low-resolution grating can capture the CN violet band and the green of C2. Calibrate wavelengths with a neon or argon lamp if you have one, with skylines if you do not. Flux calibration is hard. Relative line strengths are still valuable if you keep your instrument and reduction chain unchanged between nights. Label everything. If you're lucky enough to snag CO2 or CO in the near IR with a small spectrograph, triple check telluric corrections, most pretty NIR spectra are lies without them. If you are more radio than optical, consider 18cm OH with a modest dish. It is not trivial, but it is not a fantasy, and a weak broad line that follows the comet's Doppler track over a week will teach you more about molecular physics than paragraphs like this ever will. If you're more plasma than photons, use public solar wind data and propagation models to make your own forecast of when a sheath or cloud might reach the visitor's longitude and radius. Share it with imagers who can actually look, and accept thanks later if the kink shows up on schedule. Coordination is a technology of manners. If you plan to watch at 2 to 4 UT from Spain, post that intention. Someone in Chile may choose 5 to 7 UT to stitch a longer light curve. If you discover a kink, share your raw and processed frames, not just the annotated crop with arrows, and include the plate scale and the anti-solar angle. If you see nothing, say nothing, rather than no phenomenon. Nothing from 5 locations is bounding, not boring. If you are the person who can make a simple shared spreadsheet or a Slack with channels for imaging, photometry, and a spectra and space weather context, be that person. The value you add is not dramatic, it's frictionless. Expect to be wrong in public and decide in advance to be gracious when corrected. If you mistake a gradient for a tail kink because a bright star slid through your aperture, a kind stranger will tell you. Say thank you and remove the dot from your map. If you calculate AFRHO a factor of 2 off because you forgot to correct for phase angle, and someone shows you an equation, say, I see it now, equals the speed at which a group learns is set by the speed at which it forgives and corrects. Fold the ground back into the sky whenever you can. The same logbook that holds your comet notes can hold your personal earthquake preparedness checklist. Water, food, meds, documents, flashlight batteries. The same habit of reporting uncertainty honestly will serve you, whether you're posting a magnitude estimate or talking to a neighbour about risk after an aftershock. The same suspicion you bring to a too clean comet image should greet a too confident link between magnetometers and tectonics. All the while, resist the temptation to make the moment bigger than it is or smaller than it deserves. 3-Eye Atlas will not change your life unless you let the work of watching change your habits. A bright nova is not a portent, it is a teacher. A geomagnetic storm is not an omen, it is an energy budget written in aurora. 2 mid-6 earthquakes are not a conversation, they are a cluster obeying stress transfer, friction, and time. The bigness here, if there is any, lies in the fact that we can now watch all of these at once with instruments on 2 planets and a million quiet screens, and then tell each other gently what we saw, what we think it means, and what we still don't understand. If, at some point in this stretch of months, you get to stand under a sky where the green ribbon breathes and a faint fuzz sits near a star you can name, and a meteor slices a short diagonal through the corner of your vision, hold the image long enough to write it down after you go inside. The page is not the thing, the page is the hinge between seeing and knowing. In the morning you can turn it into numbers if you like. At night you can turn numbers into an invitation for someone else to look. Somewhere in that exchange between spreadsheet and sketch, between ephemeris and cold hands, you will have built your own small laboratory, and it will run whether or not anyone else believes that the week was weird. It will run on curiosity and calibration, 2 fuels you can store for years without spoilage, and it will never ask you to hurry. When the Mars data land, read the captions and then the methods. When a preprint claims a tail disconnection tied to a predicted field rotation, check whether the window was pre-registered. When an observing group publishes alpha evolution with cartoon confidence bands, look for the table in the appendix where they list apertures, sky annuli, and phase corrections. If a plot looks too good for October, remember that October is messy and the best curves reflect that. If work or weather interrupts, step back in without apology. One of the reasons to build a cadence is so that the absence of a point does not ruin the curve. Another is to learn by doing how often nothing is exactly the right answer. There will be nights when a cloud sits stubbornly over only your town. There will be mornings when noise swamps your spectrum and you suspect your grating is a prank. There will be days when the aurora clock says any minute and the magnetometers are flat. Keep showing up, not because a prize waits at the end, but because this is the kind of craft that counts gentle repetitions, not heroics. And when this season ends, as it must, resist the anxiety that a story is closing. Calendars fix that for free. There will be another comet and another cluster of storms and another pair of earthquakes that remind people in a particular valley to strap their shelves. 3i Atlas will be gone, but the worksheets and code notebooks and first principles back of envelope scribbles you made this autumn will still be on your desk, suddenly useful again for a different visitor under a different sun. The person who opens them will look like you, but just a little more practiced. That, not coincidence, is what time is for. Science moves forward when you decide in advance what an answer would look like and then accept it when it arrives, even if it's boring. For a visitor like 3i Atlas, that means turning a season of ad hoc observing into a planned inference problem. Begin with a data model, not a press release. You have heterogeneous streams, Earth-based photometry in standard bands, magnitudes as a function of aperture radius and time, low and high-resolution spectra, line fluxes, equivalent widths, and line profiles for CN, C2, NH2, OH, CO, CO2, OI. Narrowband images of the ion tail, position, angle and curvature. Polarization measurements, degree and angle versus phase. Astrometry, for orbit and non-gravitational terms. And, from Mars, a sparse set of images/spectra with different phase angles plus in situ solar wind context from MAVEN. Wrap these in a common clock UTC, a common geometry, a Sun-Comet observer phase, antisolar vector, projected kilometers per arc second, and a common set of uncertainties that include photon noise, calibration error, and systematics, flat field residuals, telluric corrections, scattered light. Treat the coma with a forward model instead of a folk model. A minimal pipeline is choose a neutral outflow law, Hazer, or a Monte Carlo vectorial model. Choose production rates Q of T for species of interest. Adopt a grain-size distribution and scattering phase function for dust. Propagate to a brightness field, convolve with each instrument's PSF, and compare to the actual frames through a likelihood that knows your noise. For ion tails, couple a simple draping model to a Parker spiral field with parameters as drawn from a propagated L, 1/MAVEN measurements, and MHD forecasts, NLEL/EUH Fourier. Then allow for field rotations and pressure pulses. If your forecast says the tail angle theta t should swing by delta theta over delta tt when a sheath arrives, that is a prediction you can check against hourly fits to the tail ridgeline from multiple sites. Do not retrofit, timestamp the forecast. Orbit fitting deserves the same discipline. Fold all usable astrometry through a cometry force model that parameterizes non-gravitational acceleration with A1, A2, A3, radial, transverse, normal, tied to a standard GR outgassing law. Track whether adding Mars-side parallax changes the posteriors. If A2 shifts after perihelion, while A1 stays steady, that hints at jet geometry rather than a global change in activity. If adding a rotation torque term inferred from light curve periodicity improves the orbital fit prospectively, you've connected two datasets with physics rather than adjectives. Hierarchical statistics lets you use everyone's small telescope without pretending they are big ones. Put nightly QT estimates for CN or OH from many observers into a Bayesian hierarchical model with per observer offsets and scale factors, so you learn the shared time trend while downweighting outliers. Do the same for AFP at a fixed projected radius. Posterior predictive checks, simulating synthetic observations from your fitted model and comparing them to withheld nights prevent you from loving a model that loves only your training set. Cross-validation across instruments and planets is the unpaid referee you want on your side, fit to Earth data, predict Mars brightness at the same UT and phase, and measure the miss. Synchronize clocks before synchronizing conclusions. A surprising fraction of signals die when you correct timestamps, light time and phase angle. Every record in your table should carry mid-exposure UTC, exposure time, light time corrected comet time, phase angle, solar elongation, anti-solar PA, plate scale and calibration method. For spectra, keep the air mass and the standard star used. For polarization, the calibrator and instrument position angle. You will not believe how often saving this metadata buys you clarity at the price of a few kilobytes. Adopt falsifiable metrics early. Examples: 1. Tail. P. A prediction skill. Mean absolute error less than 5 degrees for 3 consecutive nights around an expected field rotation. 2. Ionopause standoff change. A measurable inward motion greater than X kilometers, coincident within plus or minus 2 hours with a modelled pressure pulse. 3 production rate ratio trajectories. A monotonic trend in CO2/H2O versus AR that matches within uncertainties from Earth and Mars. 4. Non-gravitational acceleration drift, delta. A2 over sigma delta A, 2 greater than 3 after perihelion, with a sign consistent with the dominant jet's PA. 5. Rotation period torque. dP over dt, consistent in sign and magnitude with the lever arm inferred from jet morphology. If none of these clear your preset bars, that is a result. Call it that. Systematics are the termites in this house. Build for them. Flat fielding errors mimic shallow Kome. Uncorrected fringing in the red fakes. OI and weak C2. Under-subtracted skyline residuals invent variability. Tellurics masquerade as CO2. Star trails through apertures create false kinks. Quantify these with calibrations and with dumb tests. Rotate the field, dither, change aperture radii. You reduce with a second independent pipeline. Have 2 people blind reduce a subset and compare numbers. Keep a graveyard of dead ends and wrong turns in your repo. Future you, or someone not you, will bless that folder. Pre-registration isn't just for clinical trials. Put a brief plan in a public gist or note. Which days you'll observe, which filters, which apertures, which metrics will count as support for which hypothesis, and how you will handle multiple testing. It inoculates you against the garden of forking paths and makes your later claims legible. Pair this with open data, a lightweight CSV with columns for date, UT, filter, aperture, flux, error, seeing, air mass and geometry, plus the raw frames in a simple tree. Lets others recompute your AFP or refit your lines. If you wrote code, publish the notebook, not screenshots of plots. Data assimilation can be your bridge between heliophysics and comet physics. Run an ensemble of solar wind states conditioned on L1 and MEVEN inputs, propagate them to the comet's longitude/radius, and for each member, drive your tail angle and ionopause models. Weight the ensemble by image-based errors on tail PA and standoff distance. The posterior over solar wind parameters at the comet gives you a de facto in situ estimate. If your posterior prefers a southward Bezier by -6 nanotesla over 3 hours, and Maven recorded -5 nanotesla with similar timing, your windsock earned its keep. Don't shy from negative controls. Pick a set of quiet days by solar indices, low Ke, stable Bs, and verify that your tail angle model reduces to the expected Parker spiral geometry. Pick a set of busy days with poor space weather forecasts and confirm your comet metrics do not light up spuriously. If they do, it's your pipeline, not the sun. The red team is you, but meaner. Before you write a sentence that begins clearly, ask what evidence would make you delete it. If you can't name such evidence, delete the sentence now. Have a collaborator whose job is to break your plots. Swap calibrators, change PSFS, rebin apertures, alter telluric corrections, jitter timestamps by a minute, replace your background annulus. If the result flips, admit that and fix the sensitivity. The goal is simple. When a reader who wasn't at your telescope lands in your repo 6 months from now, they should reconstruct your figures and your doubts. We tell the truth most cleanly when we also tell the limits. Interstellar visitors are generous in what they reveal and stingy in what they resolve. 3i Atlas will give you ratios and trends and a handful of coincidences where geometry lets you see plasma draw lines on the sky. It will not give you a picture of its nucleus, and most of your claims should be sentences that begin, given model M and data D, the parameter theta sits here, with this error, not paragraphs about what an alien snowball would want. Edge cases are where instruments and imaginations go to be tested, and this apparition has room for several. Fragmentation is the first temptation. A hyperbolic active body can shed a small piece under thermal stress, rotational spin-up, or differential outgassing. The signature is a point-like condensation leaving the head on a slow diverging track with its own microcoma and a shared tail direction. The photometric light curve will show a step or a shoulder, and non-gravitational terms may twitch. False positives abound, field stars projected on the coma, cosmic rays, bad pixels. The cure is parallax and persistence, 2 sites, 2 nights, consistent motion. Another edge case is unusual chemistry. A coma rich in CO and CO2 relative to H2O at small r would be a headline in the small world that cares. Distinguishing that from telluric contamination and instrument drift is a slog. It means reference stars, A and G standard calibrations, telluric division with real water vapor profiles, and consistency between Earth and Mars-side spectra taken at overlapping air mass equivalents, anomalous nitrogen N2+ bands, or rare isotopologues would be rarer still and demand higher resolution. If you claim them, bring line lists, instrumental profiles, and Bayesian evidence, not just enthusiasm. Rotation can get weird. Outgassing torques can push a nucleus toward non-principal axis rotation, a tumble. The coma signature is a periodic jet morphology and a light curve that refuses a single period solution but yields a beat spectrum. Period drift, dp/dt, that flips sign around perihelion is not exotic. Aperiodicity that grows toward chaos is. If you see that, hold it up against AFR and production rate curves. A torque without fuel is a ghost. Soft X-rays from solar wind charge exchange are a frontier for a visitor like this. It's faint, but Chandra/XMM can, in principle, detect a halo whose surface brightness maps the overlap of wind ions and neutral gas. A detection would validate your mass-loading inference and tie the comet's soft X-ray morphology to solar wind composition in a way no other ground-based technique can. The catch is scheduling and background. The sky is bright in soft X-rays for many reasons. If you try, pre-compute expected count rates with realistic G-factors, and do not be embarrassed by an upper limit. Limits are physics. The dust environment is a practical edge. Mars orbiters pointing off Nadir toward 3i Atlas have to check that the line of sight doesn't cut through dense meteoroid streams at odd geometries, but at tens of millions of kilometers, the risk is essentially nil. Planetary protection alarms do not ring for hyperbolic passers-by at greater than 1 astronomical unit. The hazard lives in interpretation, not in the sky. You will hear about meteor streams and dusting Earth later. For a hyperbolic object like 3i Atlas, the orbital geometry does not build a resonant trail that Earth can plough years later into a shower. Some dust may fall into heliocentric orbits that, by accident, intersect Earth in the distant future. That is not a prediction you can responsibly make now, and the phase space is large. If anyone claims a new shower imminent from this object, ask them for the energy distribution and radiation pressure parameter beta of the grains, the ejection velocity field they assumed, and the integration they ran. Then watch the claim dissolve into the air it came from. A seductive frontier is biosignature-adjacent chemistry. Complex organics, CHO-enriched grains, weak bands from PAH-like structures, glycine claims in radiolines, float through the comet literature and will arrive here too. The requirements for credibility are old and stern. Line identification at multiple transitions with the correct relative strengths, independent instruments, and controls that debunk tellurics and baseline ripple. A single shallow bump at the right wavelength is not life, it is noise with good timing. Responsive astronomy, pointing big things at small targets quickly, is the infrastructure we build in the wake of visitors like this. The experience of slewing Mars orbiters off target for a handful of pixels will mature into SOPs and checklists. On the ground, target of opportunity triggers at major observatories will have interstellar visitor boxes to tick, with default exposure sets in near IR for CO2/CO and optical for CN/C2. Small spacecraft concepts will migrate from whiteboards to proposals, a rideshare 12U with a narrowband camera and a small spectrometer, parked in a heliocentric orbit ready to fly by within weeks when the next hyperbola appears, broadcasting tail angles and line fluxes as open telemetry. The most expansive edge is cultural, getting heliophysicists, cometry scientists, seismologists and variable star observers into the same Slack without turning it into a shouting match. You can make headway here with small etiquette. Label speculation, tag discipline, cite data, correct gently, bring numbers. The reward is faster triangulation when the sky and the ground are both busy. A magnetospheric physicist can point to a sector boundary crossing in a plot the moment a comet imager posts a tail kink. A variable star observer can grab a nova spectrum while the rest of us are in the backyard. A seismologist can drop a Coulomb stress map that explains an aftershock cluster without invoking the sun. Finally, do not be afraid to ask for more than the sky. Ask for better tools. Ask for a small open L5 Sentinel that stares sideways at CMEs, so we are not guessing their 3D shapes. Ask for stable funding for public archives so your raw frames don't die behind a broken link. Ask for journals to accept registered reports in observational astronomy, so plans get reviewed before weather does. Ask for citizen science platforms that treat amateurs like co-authors by default when their data shape a result. Ask for the next generation of students to be taught that pre-registration, error bars and graceful retractions are not chores but craft. If 3i Atlas surprises you, document it without dramatizing it. If it behaves, celebrate the patience that let you see the small changes. In both cases, the edge of the map is not a cliff. It is a line you would draw with better pens and steadier hands. Build the commons before you need it. That's the quiet rule that sits under every successful campaign to watch the sky together. Start with infrastructure you can touch. A place to put data where it won't vanish when a laptop dies. A place to put questions where they won't vanish when a social feed scrolls. A simple repository with folders named by UTC date and subfolders called images, spectra, calibration, notes will carry more weight than a logo. Every file needs a name that makes sense 6 months from now. 2025-10-03/UT_L_filter_120 seconds _1x1_FWHM 3.1 arcseconds.fit. If your camera doesn't write honest fits headers, keep a sidecar.json with the missing pieces. Target name, RA/DEST, phase angle, anti-solar position angle, air mass, temperature, focuser position, filter ID, observer initials. The future version of you and the stranger who wants to reproduce your result will bless the extra kilobytes. Redundancy is a kindness. 2 people should know how to log into the place where you store raw frames. 2 people should know the password to the place where you publish plots. 2 people should be able to run the pipeline that turns frames into magnitudes or spectra into line fluxes. Their versions should be tested against each other once a week in a ritual you can call Red Team Hour. Put a tiny changelog at the top of each notebook. What changed, why, and when. Bus Factor 1 is an elegant way to fail. If you're building a network that includes classrooms and clubs, design a ladder anyone can climb. First rung, look and note. A printed star chart with daily positions for 3i Atlas, and a simple form where students record date, time, location, sky condition, and a quick sketch. Second rung, DSLR on a tripod, 3 to 10 second RAW exposures, stack later with free software, annotate with UTC and lens focal length. Third rung, small tracking mount, photometry and a standard band, teach what a comparison star is and why their magnitudes matter. Teach aperture, inner and outer sky annuli, and the reason you don't move the goalpost between nights. Fourth rung, a low-res grating on a small scope, show how the CN band pops and why you must divide out telluric bands, show how you derive relative line strengths even if flux calibration is too ambitious at first. Fifth rung, polarization. Teach that a polarizing filter at a few rotation angles and a fixed phase angle can sketch grain physics if, and only if, you're pedantic about geometry and background. Urban ski does not have to be an apology. Comets and ion tails survive in the narrow band even under sodium glare. Nova spectra laugh at light pollution, because lines are where the truth is. If you can't see stars, you can monitor magnetometers and plot Kp dst and the local H component as a function of time while someone else under a better sky images. Pair each urban site with a rural buddy, and you have a 2-station experiment with a human name. Accessibility isn't a flourish, it's a feature. Sonify magnetometer data so a blind observer can hear substorms as baselines and auroral currents as tremolo. Sonify tail angle time series so a class can hear a field rotation as a slide rather than squint for a slope. Pair sketches with alt text. Pair plots with brief text that explains axes and units in plain language. Translate your quick guides. If a teenager in Caracas can read your how to log a magnitude sheet in Spanish on a phone with a cracked screen, you did it right. Moderation is the boring magic that prevents good projects from collapsing under their own success. Write down a code of conduct in 4 sentences. Be kind, label speculation, cite your sources, correct gently. Appoint moderators who can nudge a thread away from astrology and toward apertures without starting a fight. Keep a myth parking lot, where persistent misunderstandings live with gentle debunkings everyone can link instead of retyping anger. Post a weekly digest that celebrates work and services needs. We still need coverage 0200 to 0400 UT on the 21st. We're short on our filter data. We have 3 spectra but no telluric standards. If you must fight misinformation, fight with posture and receipts. Treat the person, not the claim, with respect. Offer numbers anyone can check. The dust tail curves because radiation pressure pushes small grains. The ion tail is straight because ions track the magnetic field in the solar wind. Here's how you can see the difference tonight with binoculars. Works better than that's wrong. If someone insists 3i Atlas is a harbinger, give them the calendar, the dates of perihelion, Mars near pass, Earth's geometry, the history of the 2 previous interstellar visitors, the statistics of CMES during solar maximum. Invite them to watch, not to believe. Credit should be a habit, not hero worship. If an amateur's image anchors a figure in your paper or report, put their name under the panel and in the author list if your journal allows it. If a student's method rescued your analysis, let them narrate that section in their voice. If your pipeline stands on public libraries, cite them in the text, not just in italics at the end. When in doubt, overcredit. It builds a culture where contributions have weight beyond applause. Light pollution is a backdrop you can engage with. Map your community's sky brightness by neighbourhood with SQM meters and post the results. Make it a civic project with a simple ask: shield the lights you control, talk to your building manager about colour temperature, celebrate the park that went warmer and dimmer and made Orion possible again. Keep a list of dark hour windows when local sports fields are off and public lighting is lower. Schedule your public observations in those windows rather than fighting the stadium. Night safety is logistics. If you're inviting people to observe, pick a location with sightlines and parking, post a map with red light safe routes, have a buddy system, bring insulation and extra red lights. If you're in wildlife country, know the rules and respect them. If you're inviting families, put the bathroom situation in your event description. If you're meeting in a city, talk to local authorities so no one calls the police on a group of people carrying tripods in the dark. Archiving needs a spine. Put your raw frames in a public bucket with checksums. Mint a DOI for each night's bundle. Write a human-readable README in each directory, so a curious person doesn't need to speak fluent fits to understand what they're looking at. If you have the patience, mirror to 2 places so one institutional change doesn't take your year with it. The rubber meets the road when someone months from now can remake your AFP plot with only your archive and a browser. Interdisciplinary bridges are built out of specifics. Invite a heliophysicist to your comet meeting, but ask for something precise. Help us predict Bezier at the comet's longitude on October the 29th with 2 models. We'll test tail angle predictions against our images. Invite a seismologist to your community call, but make the ask concrete. Explain ETAS with 1 slide and show how we'd use it as null to test any claims about space weather. Invite a NOVA person and ask for what line widths and profiles tell us about shock velocities in gamma ray novae. Here are our spectra. If you can, build a small cheap sky monitor that watches all night from a school roof, a fisheye camera with an all-sky lens, a Raspberry Pi, and software that time-lapses clouds and catches aurora. Pair it with a tiny induction coil magnetometer that logs the H component while you sleep. Post both streams live. Let students clip their own segments when a substorm peels the oval south or when a cloud front ruins a night beautifully. The apparatus is as much pedagogy as censor. Governance matters once you grow. Decide who decides. A simple rotating steward team can keep your project nimble. 1 astronomer, 1 educator, 1 engineer, 1 student, 1 community organiser. Meet monthly with a short agenda. What went well, what needs attention, what to archive, what to drop. Publish notes. They don't have to be Shakespeare, they have to be visible. Fundraising does not need to be awkward if it is honest. A line for storage fees, a line for small gear grants, a line for travel scholarships to let a student present a poster, a line for accessibility, captioning, interpreters, translations. Show where every dollar went with the same clarity you bring to your error bars. Set enough amounts, not infinity amounts. Treat art as a method, not decoration. Commission 3 people, a painter, a musician, a poet, to interpret the Ion Tail's swing over a week. Host a tiny show where their pieces hang next to the tail angle plot, the magnetometer trace and the narrowband image. Let a class write a choral piece that crescendos when the Ion Tail disconnects. Map the nova light curve to a piano roll and listen as hydrogen recombination quiets into a lower key over days. You'll be astonished who shows up for science through a different door. Keep a faults and lessons ledger that is as rigorous as your glossy page. Log the night you forgot to rotate your polarizer. Log the evening you pointed at the wrong comet and still learn to plate solve in a hurry. Log the weeks you fought with fringing and the person who fixed it by dusting the filter you swore wasn't dusty. Transparency about fallibility is the most generous gift you can give a newcomer. Carry forward a curriculum compact enough to live in a backpack. A field guide printed on 2 folded sheets. How to estimate magnitude, how to choose an aperture, how to note the anti-solar angle in a sketch, how to compute a FPRO, how to read a magnetometer trace, how to check if a tail kink lines up with a field rotation, how to file a minor planet center astrometry report without fear, how to write a 3-sentence observing note that a professional will actually use, translate it, print it, laminate it, hand it out like candy. Clear questions are a relief in a season that makes people feel like everything is talking at once. It helps to collect them all in one place and refuse to decorate them. There are the obvious ones, the ones you can answer with a plot and a few sentences. How quickly does the ion tail of 3I Atlas respond to a strong rotation of the interplanetary magnetic field? What is the typical standoff distance of the ionopores at 1.4 astronomical units for your ECO2-dominated coma under a 400 km per second 5 nanotesla wind? Do Cn and C2 production rates rise or stall near perihelion? And by what factor relative to water? Does the non-gravitational transverse acceleration A2 change sign after perihelion? And is the magnitude consistent with the spin state inferred from jet modulation? If a tail disconnection occurs twice in a week, what is the cadence between the onset and the reformation of a steady ion tail, and how does that compare to sheath transit time in propagated models? There are the nerves dressed as questions, the ones you address with scale and humility. Does a G3 geomagnetic storm change the probability of an M greater than or equal to 6 earthquake anywhere? What size of stress perturbation would be required at depth to measurably change an aftershock decay? What's the energy budget for a nova's soft X-ray phase, and how many extra joules per square metre does Earth see at the top of the atmosphere? How many novae brighter than magnitude 6 occur in a decade, and how often do 2 fall in the same week? There are the long questions that don't expect a tidy answer this year. Are interstellar visitors compositionally diverse in ways that mirror the exoplanet demographics of their birth systems, or do selection effects bias us toward a narrow class of survivors? Do CO-rich, water-poor comae at small heliocentric distances correlate with particular stellar nursery environments? Do tail disconnection statistics during solar maximum differ in rate or morphology from those during declining phases when the heliospheric current sheet is flatter? Does the polarization phase curve of dust in 3I Atlas differ in slope enough from Jupiter family comets to demand a different grain formation history? There are technical questions that look like chores until they decide to be breakthroughs. Can you train a computer vision model to extract ion tail ridges robustly from noisy, star-crowded fields and return position angles with less than 2 degrees error? Can you assimilate Earth and Mars-side tail angle data into an ensemble MHD model to invert for field orientation at the comet without in situ magnetometers? Can a network of shoestring magnetometers in schools produce a credible map of regional storm time disturbances that correlate with HF radio outages in a way pilots can use? There are questions you pose to yourself because they keep you honest. What precisely would disconfirm your preferred reading of that tail kink? If the Mars spectra contradict your Earth spectra by 30%, will you spend a week repairing your telluric correction before you write a paragraph? If your AFR curve rises nicely across perihelion, but your non-gravitational acceleration refuses to match the required torque, will you admit your phase correction is wrong? Or will you compose a hymn to exotic outgassing laws? There are proposals hiding inside questions. What would a modest L5 monitor dedicated to CME 3D geometry cost if you stripped it to the bone? A coronagraph without a press office but with the open telemetry? What set of standardized rapid interstellar visitor scripts should the big facilities keep on their desks? CO2/CO near IR templates, optical CN/C2 sequences, polarization blocks, so a TUU isn't a scramble. What small sat could you reasonably build to meet a hyperbola halfway, a 12U with a narrowband imager, a compact UV spectrograph, a star tracker you trust? And what orbit would you want it in so it can wait without great expense? There are cultural questions we seldom write down because we think they are soft. How do you teach a group to love error bars? How do you structure a call so a high schooler isn't intimidated out of speaking? What percentage of your airtime should be drawings, and what percentage should be equations if your goal is to keep both the painter and the physicist listening? If you teach, there are kits to build from these questions. A week-long module called A Week of Sky that mixes meteor counts, magnetometer sonification, comet sketches, and a one-line spectral measurement of CN, a semester-long project where students pre-register a tail-angle forecast for 3i Atlas on 3 dates, then test it and write the result no matter what. A storytelling night in which each person brings one graph and one sentence, and the rest of the time is questions. A pattern diet worksheet that names the Texas sharpshooter fallacy and the availability heuristic and gives you one healthy alternative: absolute dates, base rates, pre-committed windows. If you plan media interactions, there are protocols that keep your science intact. Always say the dates. October 3rd for Mars geometry, October 29th for perihelion, December 19th for Earth's closest. Always say the magnitudes in both senses: how bright, how big, how uncertain. Always say what you would accept as disconfirmation. If we don't see a tail rotation within plus or minus 3 hours of the modelled field swing, we'll revisit the wind propagation. Ask for copy review on technical points. If you can't get it, write a short what we meant note to publish on your site the day the story runs. If you love lists, there is a research agenda you can print and tape above your desk. Measure the rotation period and its drift for 3i Atlas. Measure CO2/H2O and CO/H2O near perihelion from Earth and Mars and reconcile them. Map tail disconnection times against propagated sheath arrivals and field rotations. Quantify misses. Derive an ionopause standoff curve versus heliocentric distance and upstream pressure. Publish the constants. Detect or set up a limits on soft X-ray emission from solar wind charge exchange in the coma. Fit non-gravitational A1, A2, A3 with and without a torque model. Report the Bayes factor to that prefers one. Train and publish a tail angle extractor. Make the code public. Publish a registered report of your observing plan and then a follow-up report of how reality differed. Leave both up even if the second is boring. Draft a one-page L5 Sentinel concept. Draft a one-page small-sat flyby concept. Write a school-friendly how to observe guide in your city's top 3 languages. If you need the long arc, there's a set of future doors you can name without knocking. Rubin Observatory will come fully online and pour a waterfall of transient alerts into the world. Your group can be the sieve all for cometary weirdness if you prepare. NEO. Surveyor will watch in the infrared for small dark things. Its catalogue will catch faint motion that backyard people can harden into orbits. A mission will go to an interstellar visitor on purpose. Until then, it's all about improvisation. There will be a year with no naked eye novae, and a year with 2. There will be a week with a G5 and a season of quiet ovals. The pattern is that there is no pattern, just base rates and clocks, and the habit of writing down what happened when. If none of that fits on your table, reduce it further. Keep a log, share a plot, ask a better question next week. The person who finds a quiet, clean way to measure the ion tail's angle on 3 nights during October will have done as much for the map as the person who wrangles a spectrograph in Mars orbit. The lineage of care is long and local. Observers under suburban skies, coders who refuse to tolerate fragile scripts, teachers who show students that real graphs have noise, moderators who steer away from fights, translators who put a sky into a language, and someone you will never meet who opens your raw frames at 2 a.m. because their curiosity felt like yours. If you still need a sentence to hold in your mouth when you go outside, the fields are invisible until a bright, fragile thing threads them. 3i Atlas is one such thread. It is not a sign. It is an instrument we did not build and could not buy, passing through a laboratory large enough to share without tickets. The lab runs whether or not you are there. It will run again when something else wanders in. The question is whether, the next time it does, you already have your place at the bench. A notebook, a plan, a friend to check your math, and a small consistent promise to pay attention. If you're still here with me, Night Owl, take a breath. Let your shoulders drop. The sky will keep doing what it does whether we're watching or not, but tonight We watched together. We mapped bright novae and quiet error bars, earthquakes and aftershocks of ideas, solar storms that write with invisible ink, and the fragile cometary windsock we've been following, 3i Atlas, threading it all. The theme wasn't doom, it was discipline and wonder at the same time. Label what's measured, label what's modelled, label what's merely possible, and then go look again. Here's what I want to leave you with. You don't need perfect gear to belong here. If you have nothing but your eyes, you can still step outside, let them adjust and notice which stars clear your horizon now that didn't a month ago. If you have binoculars, you can trace a faint coma and a tail and sketch it with the anti-solar direction marked. If you have a camera, a tripod and 10 seconds of exposure, you can stack a handful of frames and rescue a whisper from the noise. If you have a telescope, you can measure brightness through a fixed aperture and write down a number the rest of us can use. If you have a spectrograph, you can catch CN and C2 and turn colours into chemistry. If you have code, you can teach a computer to find tail ridge lines or fold solar wind models through simple geometry. And if you have a classroom, you can turn all of this into a week of sky that someone remembers for years. Keep the dates in your pocket, not as omens, but as invitations. October 3rd for Mars's Vantage on 3i Atlas. October 20th to 21st for New Moon Darkness and Orionids cutting cleanly through it. October 29th for perihelion heat and whatever that stirs. December 19th for Earth's nearest geometry. If you go out on any of those nights, take a notebook or a notes app and write down the UTC time, the seeing in your own words, one thing you noticed and one thing you still aren't sure about. That little ritual is how stargazers become observers. If something in this journey helped you drift off a little easier, or wake up a little more curious, tell me below where in the world you're watching from and what the sky looked like tonight. Share your sketches, your tail angle plots, your nothing happened notes, those matter, your aurora photos with honest histograms, your failed attempts that taught you more than a pretty picture ever could. If you're new here, this sleepy corner of the internet runs on slow science and good manners. Hit subscribe, tap the bell, and you'll fit right in. If you've been with me a while, you know the deal. We don't chase sensationalism, we chase signals, and we're happy when the signal is small and real. A few promises I keep to you and to myself. I will keep naming sources of uncertainty out loud. I will keep separating we saw from we think. I will keep reminding us that a G3 geomagnetic storm can bend an ion tail and your radio, but it doesn't reach through rock to steer a fault. I will keep pairing beauty with baselines, and I will keep making space for all the ways of being here. The painter who hears a disconnection event as a sudden rest in a score. The physicist who hears it as reconnection in a rotating field. The teacher who hears it as a lesson plan. The student who hears it and says, "Show me how to measure that." Say goodnight to the idea that you need permission to take part. You don't. The lab is open, 2 planets wide, 1 million windows tall, and 3i Atlas is just tonight's fragile instrument in it. Tomorrow there will be different instruments, a meteor shower, a storm, a variable star, a quiet magnetometer trace that dips when Aurora breathes. Bring tea, bring a sweater, bring your patience, bring your questions, bring whoever in your life could use a reminder that the universe is not shouting, it's whispering, and we can hear it if we get closer. Before you go, take one last look out the window, or up from the sidewalk if that's the sky you have. Find a star. Give it a name you'll remember. I'll meet you under it next time with a new map and the same rules. Be kind, be curious, be clear. This has been the Sleepy Voyager, and you've been the best company. Sleep well, travellers. When you wake, the sky will still be there, and so will your notes.